have made a lot of contributions to things like something that obey Michaelis-Menten kinetics, which are these so-called nanocages, to understand chemical reactivity under confinement, or the role that electric fields can actually play to help us understand how these activation barriers are lowered in the presence of a scaffold, of a protein scaffold. And finally, which is that there's a very hot area right now of microdroplet chemistry, simple water droplets that seem to accelerate common organic reactions by anywhere between 1 to 6 orders of magnitude compared to the bulk phase. And so that's actually sort of a kind of a current mystery that's trying to be solved. And so to deal with all of these systems, okay, we have to work with pretty expensive ab initio methods. And I wanted to kind of illustrate then what has to go into this, right? Which is that let's take these nanocages, and I want to recognize Valerie, who is a former postdoc, who's now an assistant professor at Virginia Tech, and then this Wan Lu is phenomenal. She's a current postdoc in the lab, and she's an ACS fellow. And together, they worked on trying to understand these small environments that seem to obey Michaelis-Menten kinetics and tend to sort of be argued to be protein-like, to be able to understand those rates and in particular mechanisms, and understanding how transition state stabilization actually comes about. And we've made sort of some efforts to try to understand those from the point of view of concepts like pre-organization of electric fields to understand them. And of course, what we have to do first is we have to go find that transition state. And so what do? Well, we turn to the techniques that have been developed by many of our colleagues. We consider the uncatalyzed and catalyzed reaction of this so-called nanocage, and we're running it in explicit water, and we use metadynamics. And then we have to worry about the underlying density functionals that we're doing, and GGAs with their delocalization errors. Can we do a little bit better with affordable meta-GGAs, but at some computational expense? And then we find a putative transition state within the reduced manifold. Then we have to go and do committer analysis, and then we look for the minimum energy path with a zero temperature string method. And at the end of the day, we actually are able to, kind of now start talking about the nature of the mechanism and the chemical reactivity of this particular synthetic catalyst. But the thing is that I'm trying to emphasize here is that this, of course, is months of ab initio workflow, right? And so, but I want to make a comment, and it's kind of something that I've been thinking a lot about recently, about just, can machine learning do better? And what I mean by that is that once you have a good physical model, those results are predictive, right? I mean, they're designed to be predictive and ready for what I would call discovery, which is, can you discover what the mechanism is? Can you get a surprise in what you discover? And the thing that I kind of worry about in regards to machine learning is the fact that they are so interpolative. And so, but let's just kind of gamely sort of carry on and try to start asking, though, which is that will they at least deliver on the first promise, okay, of reducing this incredibly heavy workflow that's required in order to make progress, especially in the area of chemical reactivity. All right, now I'm going to take a little bit of a side ways step by introducing machine learning for a different purpose, which is chemical shift prediction. And I'm doing this for the purpose that I want to kind of illustrate that as we go to certain types of architectures or certain types of representation, that it costs. It also has its inherent cost, which is that you got to generate, this high quality data. And so in this chemical shift prediction, of course, what you're trying to do is you're trying to match experimental measurements against an ab initio DFT method, and that's our order n cubed scaling that we've been talking about. Really not, scales with the number of atoms, but really with the basis set size. All right. So there's lots of calculators. What you're trying to do is you're trying to either do back calculation, which would take a structure and back calculate a chemical shift to match to experiment, or take a chemical shift and do a forward prediction to structure. In either case, these chemical shift calculators have been developed over time, and really their data representation is feature extraction. There's lots and lots and lots of attributes that experts in this area understand and utilize in being able to try to do these back calculations for chemical shifts. And so the idea here is that the data representation in the machine learning context can be feature extracted. They can be symmetry operations, and then these 3D images of the chemical environment are sort of possibilities. And as I said, which is that, if you're going to, there are different methods that are trying to deal with either having a reduced amount of data, or some that actually require lots of expensive ab initio data. And of course, the reason that you're sort of dealing with all these trade-offs between data representation and data size is that you're trying to get accuracy, okay? And you're trying to make sure that it's transferable or scalable. So these are the kind of the tensions that you're facing when you're trying to do something predictive with machine learning. Okay, so with that, here's our chemical shift, and we decided to go this 3D, this 3D representation route. And so we built this convolutional neural network, and worried about sort of type of regularization techniques that allows for good training. But the key thing here is just to simply say is that we went through with this sort of 3D representation of multi-resolution to sort of treat the resolution as different types of channels that then can be put within the context of a convolutional neural network to then make prediction on chemical shifts. Okay, so this is what we call our multi-resolution 3D dense net, and at the end of the day, we're comparing this against a kernel ridge regression method. Okay, well, why was this kernel ridge regression proposed to begin with? Well, it was because of data constraints. The chemical shifts that are being calculated are expensive. And ultimately, which is that, but that's one of their benefits, is they don't require a lot, but at the same time, they have these also order n cubed matrix operations, and therefore, can't necessarily afford as much data. And the nature of the representation, or the symmetry operations, are baked in. So what do I mean by that? I mean that the chemical shifts should be, that any predictions, any sort of 3D re-expression of the Euclidean space should be invariant to the chemical shift, and that type of symmetry operation is baked in by construction with a KRR method. Now that actually was not the case for a convolutional neural network, and therefore our multi-resolution 3D dense net. Okay, and so, but one of its benefits is that you're going to get lots of prediction accuracy, but you got to also at the same time fill it with data. And so we did something that is, is kind of a poor man's approach to this, which is to just do data augmentation, which is that doesn't cost you anything, which is you now are just going to rotate the chemical environment of your particular atom of interest whose chemical shift you want to predict. And then you can do this, you increase the data set size by roughly an order of magnitude. Okay, and when we do that, then if we can see that, obviously the convolutional neural network doesn't perform very well till you get to fairly large data of the original data without augmentation. And so, but effectively, there's not much improvement until you are able to sort of exploit that deep network through data augmentation. And we do this with whether we do the augmentation on just the data, or whether we do the augmentation as well on the test set, which is kind of doing ensemble learning. And here is where we get now significant prediction accuracy. And with that, then, just to say that these are significant improvements. Okay, so this is now starting to approach for proton chemical shifts, which is a kind of a big deal in this area of that are comparable to experiment, that are really at this point matching experimental error, at least in the solid state. And we can get significant improvements for the other heavy atom chemical shifts relative to KRR. But some of this is telling, some of this data analysis is telling us that the reason that we can't do better right now is because we have just insufficient data. So even with data augmentation, what we really need are more unique training samples. But as I've already said, which is that that's not an insignificant expense. And it's something that in order to, that we would have to come back to. And we're working with Martin Head Gordon's group, who is developing an NMR, a computational in silico NMR lab, to try to get these ab initio calculations to come down in cost and to increase their accuracy in order to be able to exploit methods like multi-resolution 3D DenseNet. So what I'm really trying to kind of emphasize here is that machine learning has a cost, right, of being able to generate these high quality data sets. And so now what I wanted to turn to then is to say, well, how in the machine learning context can we overcome that? And there's been a hot area that's been, has come about roughly over the last year to year and a half of trying to move away from these so-called invariant to equivariant models, machine learning models. And the idea is that instead of through data representation, you're going to actually try to formulate the network, the machine learning model itself to be equivariant, to be able to satisfy the fact that the transformation, okay, in 3D space are going to be built in, it's going to be baked in directly, but not through the data. And that this should therefore improve not only prediction performance, but as is being demonstrated by a number of research groups. And so we've done something called NewtonNet. There's other methods that are out there that are equivariant, Gabor-Sayani or the Harvard group, Tess Schmidt at MIT, the Shoot lab in this area, Tom Miller's group. All of these sort of methods kind of came online roughly in the last year. And what these equivariant models are going to do is to reduce the need for these large quantities of reference data. And it will, again, allow us to do kind of two things, I think. One is to essentially exploit, let's say, good DFT data well, but furthermore opens up for the possibility of the most expensive ab initio data, things that are sort of reaching wave function-based methods of things like couple cluster accuracy in the complete basis set limit. Now, our flavor of this equivariant model, the reason we call it NewtonNet, is that it actually we say that it's satisfied Newton's third law. It actually is sort of constructed to do both second and third law. And so now what we're doing is we're going to treat it's a message passing network that's going to treat environments where the force direction is a feature, it's an attribute of an atom. And that is going to, by construction, allow it to remain equivariant to these rotations in 3D coordinates. So if we wanted to, we could apply NewtonNet directly to the chemical shift problem that I just described. And by doing this, we're going to preserve this feature, this equivariant feature throughout the network. And to try to make this just a little bit more concrete, and you can go to the, and by the way, I kind of want to have a little bit of a complaint here, which is that we submitted this paper back in August, and we are having a real trouble getting journal, we have it under review, but we're just not getting turnaround. And so I don't know what's going on with with this area, but it's competitive and it's hard. It seems to be hard to essentially get this through review, and I'm just talking about getting a review. Okay, um, so anyway, going back to the this message passing network, right? So we have these iterative message passing environments. So these are sort of then kind of like LSTM like, where we're updating these atomic environments. And so, as I said, these layers, okay, so here's, this would correspond to one layer right here. We have multiple layers of these message passing environments. And as I said, they're rotationally equivariant by construction. And they consist then of these operators, these modules. And these modules then have these constructed forces and displacement. Has feature vectors of an atom. And these attributes are then constructed in such a way to satisfy both the Newton's second and third law. And the key thing is that, we don't just want to necessarily just predict forces, even though as part of an MD engine, that's mostly what matters. We also want to be able to calculate the energy. So these are contracted, these features are contracted through this energy module, because we also want to be able to predict energies as well. All right, so please refer to the submitted archive paper to see it. And one of the goals of these machine learning methods is to try to not lose too much to the abstraction, right? To essentially be able to do things that are physically interpretable. And what I'm showing here is that, through these multiple layered message passing formulations, these latent force vectors, okay, that we are trying to predict, compared to the reference force vectors, are become, well learned. Okay, so the idea is that there are part of the loss function, the enforcement, and then by the time the data is transformed through multiple layers, we ultimately reach then a cosine distance that is decreasing and ultimately becomes actually pretty very accurate. All right, so there you can sort of see it in action, okay, in regards to the machine learning. And now what we're going to do is to put it into, well, first of all, just can we actually, put it in, can we actually test it, is what I'm trying to say. And there's lots of these sort of data sets that are out there, right? These data sets that are telling us about how our method is performing. And here, for example, is that goal that I was talking about, the highest quality ab initio data, of which there's not a lot. One can get energy and force predictions with Newton net that are highly, accurate relative to invariant machine learning models, and very competitive, or even possibly outperforming in some context, things like AnyQuip. All right, and then there's the famous ANI data set, and here's where I want to start making the point that the performance of this can actually, still be significantly quite good with less data. And so what I'm showing here are just ANI is just an energy data set. So the original 20 million data points, the energy error that's been reported, okay, with a sort of a standard invariant model. Well, we can take that data down to 10% or 5% and really reach errors that roughly halve that. Has an illustration of the reduction in data requirements with these equivariant models. And the same is an example of where now we care about reactivity, and therefore we really want to know how we really need those forces. Just showing again that these a methane combustion set that was constructed by Zhang Zhang's group, using and then utilizing something like DeepMD. Well, with that same data, we can really reduce the error, and then we can even sort of decrease, okay, the data set by an order of magnitude to get something. Obviously, you're losing some, but not as much as the original method and data set. Okay, so now part of what we've done now is to start playing around with the idea of how are these things going to work in a really reactive context. And so hydrogen combustion, okay, well, that's similar to methane combustion, but the idea is that we constructed this data set because so this is something where it's our kind of the first foray to seeing whether you can get something predictive from hydrogen combustion, in particular, which is when hydrogen combustion is conducted under high pressure. And there, it's thought that these traditional models, these kinetic models that have been developed for hydrogen combustion, which is important, as we all know, for and kind of in the chemical industry context, that's where those models begin breaking down. And so the question is, can you essentially start generating high quality data, ultimately energies and forces, and then be able to simulate these things under the actual real experimental conditions of high pressure, to be able to start seeing where those models break down and why and how you might correct them. So that's kind of the motivation for looking at this hydrogen combustion data set, and I'll talk about this in just a second. But again, just to emphasize that, with a invariant model like SNET, okay, which is over here requiring some amount of data, we can surpass that with, again, a greatly reduced amount of data for not only energies, but also for forces. Okay. All right. So now with NewtonNet, we turn to this hydrogen combustion problem. Has really kind of a sandbox for chemical reactivity. And I just wanted to sort of emphasize that we worked rather extensively on, first of all, having intrinsic reaction coordinate data for on the order of about 20 of these reactions. And here I'm just showing a few, a subset of them. Okay, so there's about 20 reactions where we have the intrinsic reaction coordinate, and then from that we do systematic normal mode analysis as well as ab initio molecular dynamics to be able to sort of populate data at this level, at this decent level of theory, a hybrid meta GGA, which is sort of reasonably high quality, a pretty decent basis set, and to generate this hydrogen combustion data. And so the first thing we thought we would try is to say, well, let's see if the putative transition state of the intrinsic reaction coordinate is actually the true transition state from a free energy perspective. And it turns out that as you go through these reactions, reaction one is pretty much, energy dominated, enthalpy dominated, and because we're doing this, at finite temperature, but you start seeing that certain reactions are showing up where that intrinsic reaction transition state is not the transition state in a free energy sense. So there's some kind of entropic factor for some of these reactions. And so I'm going to focus today on reaction 1 and reaction 16 and 17, just to sort of has a contrast between the things like the intrinsic reaction coordinate and then something like this, and sort of develop this picture of trying to find the new transition states, okay, for these reactions. All right, so we did that, and what I'm showing here is that here's where the transition state appears to be adequately predicted by the intrinsic reaction coordinate itself. And so, this is so-called reaction 1, and what we can see is that we're discovering, or we're seeing with the machine-learned forces that we're predicting some ratio of reactant to product. But during that, some of those trajectories failed. Okay, why? Well, it turns out that we forgot to put in the atomization energies, right? It was just that part of the training data. It causes we don't get these species. We introduce a new thing that the machine learning hasn't seen before, which is these atomization, the fact that that there's a low energy possibility, which of course is unphysical for the molecules to atomize. All right, so you got to go back to training, and you go back to training. And so here we do the kind of the classic act of learning, right? Which is that you're well, ignore this part right here, but just focus on this act of learning, right? So we've generated this data set, and then we're doing the training, and then we do these, we find these outliers, and then we have to go back and generate new data. And so the way, of course, you do this is that you formulate 4 Newton nets with different initial conditions. And then the idea is that when you discover a new species that you didn't expect, it's going to fall outside standard deviation and therefore be picked up and signal to you that you need to go off and generate more data. And I want to sort of emphasize that the machine learning on a CPU or GPU is obviously about is under expectation about 2 orders of magnitude cheaper, okay, than doing the, and so therefore every time you have to send it off, right, you're going to be sitting there waiting, okay, as you generate the data with your ab initio method, and also in some sense, I think, kind of reducing your ability to discover. But okay, so that's the way it is. So we continue on, and so before training, we get these strange behaviors, and after training, things smooth out, and things like, the one of the basic symplectic properties gets satisfied, which is conservation of energy, and reaction 1 is finished, and now we can confirm that the IRC from this committer analysis is all doing fine. Okay. All right, so now let's turn to reaction 16, which actually doesn't determine that, it doesn't have, where the IRC is not determinate for the transition state. And now we begin doing metadynamics. Okay, so now here's, as we have putative reaction coordinates, we're following those, and over some period of time, we believe we've located this new transition state. And here's the sort of the product state and the reactant state. And so these are, so this is sort of developing reasonably well. We decided to go and look at some better reaction coordinates, and now that we're sort of pretty confident about this reconstructed free energy surface for this intrinsic, where the IRC, where we're looking for the transition state, because the IRC no longer is not supportive of that transition state, and boom, we run into a hydronium, right? So hydronium's not sort of, hasn't been trained for, and its machine learning model overstabilizes a species that should be much higher in energy. So we're back to essentially now generating active learning again. And so, so we send it off for some data, and we come back, and this is just the error now of the new species, of the hydronium. So we don't have a lot of this new hydronium. I don't know, we have something like 1,000 snapshots. And these are the kind of errors that we got to tolerate until we can continue to discover more and more potential species, okay? For example, the new transition state, which we don't necessarily have, has part, where we have to, continue training and training and training with this active learning procedure. And, clearly we need to continue generating a little bit more data, even though Newton Net requires less data. It's not, a panacea for very little data. And so, we're starting to get some compromise then on force prediction. And we're just going to have to keep generating more and more data in order to improve these predictions. All right, so then going to reaction 17, and just to simply say that, interestingly enough, it just rediscovers reaction 16, right? Because they both essentially have the same product channel. Okay, so the kind of the thing that I'm kind of, then the last thing just to say is that, when we actually discover this new channel, we can see this in the energy, and the question is that instead of using these machine learned models, many instances of those, perhaps we can essentially just use energy conservation as a different type of active learning strategy, which would be, I guess, less onerous in some ways, in order to essentially signal when we have to go back and train with more data. So I'm going to stop now and conclude with a few conclusions, and also a few points about the future of machine learning, at least from my point of view. I think that they do have a lot to offer, chemical reactivity, but really in the actual, I mean, other than inventing methods to predict energies and forces, I think it's quite a different matter about whether they actually work in the MD engine context, okay? And just not even just the MD engine context, but for any kind of real chemistry. And so, you know, having lots of expensive ab initio data, you know, great, we can predict with ab initio accuracy, but that data comes at a cost. And these equivariant models are really important because they really are reducing our needs for data. And in a way, they are suitable for active, you know, they're necessary, in fact, if we have to continue to do active learning, to do anything of complexity. And that really this is the next frontier. This is what I tell my students who want to work in this area, is that it is really kind of the, I think, is the Wild West out there for really making machine learning engines, MD engines, actually work, okay? And to really, when my postdocs are trying to sort of move fast, and I feel very slowed down by these ab initio methods, and they're eager to turn to machine learning, it's just not ready yet, right? We've got it's a frontier that has to essentially be tamed and to make accomplishments. And so I think that's where I will end, before, of course, thanking my wonderful group. During COVID, they have been literally phenomenal. And so I've been very lucky. I feel very, I do feel privileged to work with this group because of, like I said, they've handled COVID so well. And then, of course, I'd like to thank especially, Mashtaba and Jerry and Nancy. Where'd Nancy go? There she is. Who've, really have been wonderful, and a new student, Ufan, who's been wonderful in machine learning, and my colleagues. And I'd like to thank you very much for listening, and I look forward to taking some questions. Thank you.
Biman, you're muted, Biman.
I think they are not allowing me. So fine. Thank you, Teresa, for this wonderful talk. So now we move on to the discussion. I think Anmol Kumar asked that is CNN not rotationally equivariant? Can one CNN model trained on one set of chemical compositions be used for prediction for properties of different chemical compositions?
I'm sorry, could you say that again?
So is CNN not rotationally equivariant? That's the questions he has. And then he said that can one CNN model trained on one set of chemical compositions be used for prediction of properties of different chemical compositions?
No, I think that, I think this is true of most any machine learning method, right? Which is that it's not particularly transferable to new chemical compositions. And I think that's what I was trying to show.
Mm-hmm. He also has a different question. Is Newton net suited more for prediction of reaction dynamics, or is it more efficient for static properties as
well? It should be. It should be fine for either case. And so, yeah.
Okay, so I don't find any other question in the chat box. If someone want to ask directly, can do so.
Can I ask?
Yeah, sure, go ahead.
Thank you so much for the very nice talk, very nice results. Regarding this Newton net, is it possible to try to mimic the potential? Like, for example, in the external potential, like in QMMM calculations.
I'm sorry, I don't know why I'm having trouble hearing. If I can, if you could repeat the question again.
Am I audible now? Is it better?
Yeah, let's try again.
Okay, so what I was asking is, for the Newton net, can we use Newton net to predict the electrostatic potential?
Oh, I see.
Right, yeah.
Yeah, actually, so right now what we're doing is we're actually seeing how Newton net performs on arbitrary property. And so what I can tell you is that with, again, a fraction of the original data for, let's say, chemical shifts, the answer is yes. And then the question of electrostatic potential being an energy type quantity, I don't see why not. So it should be very extensible. It's just, we started off here in the force area. And then just to also say that, a convolutional neural network is not rotationally equivariant, at least as far as the old, the old versions. I think there's, this is a CNN. The Newton net actually is at CNN as well. Has components of CNN, and so there the equivariance has to be enforced, or has to be constructed and has to be formulated.
Okay.
But a CNN is not by default rotationally equivariant.
Thank you.
Okay, so thank you, Teresa, again for this nice talk.
Thank you.
Yeah, so now we'll move on to the next talk. Our next speaker is Dr. Matteo Salvalagillo. He is an associate professor in the Department of Chemical Engineering and Faculty of Engineering Science at the University of College London. His research interests are crystallization, nucleation, protein ligand binding, protein chromatography, new molecular dynamic simulations, and enhanced sampling techniques. So today he is going to talk about understanding how to enhance nucleation in real world graphite electrode in contact with sodium chloride solution. Matteo?
Thank you, Biman. Can you hear me?
Yeah, we can see your slide also. Fine.
Fantastic. So thank you for your kind introduction. And today I'm going to describe some work that has been done by a talented postdoc in my group who's called Aaron Finney. And it's around understanding how to control nucleation. So it builds on a lot of rare event methods and enhanced sampling simulations. It's not a development work, it's an application work, but hopefully it kind of will give a bit of insight into how these methods can be useful to relate to real experimental work and applications in this field. So the context for this work is essentially within a larger collaboration that we're part of in the UK. We are part of this consortium, which is called Crystallization in the Real World. And within this context, we are trying to understand how we can exploit the surfaces, and in particular electrode surfaces, to control crystallization. Controlling crystallization is key in a wide range of fields, including pharmaceutical manufacturing, for example, which is particularly interesting for us. However, it is extremely difficult to build a consistent parallel between experiments and theory when the length scale becomes very small, processes become activated, and there's a number of practical issues to address. So in order to develop a joint experimental and theoretical framework to analyze crystallization at electrode surfaces, we have teamed up with Professor Pat Unwin's group at Warwick, and in particular with Dr. Hugh McPherson, who's the postdoc that has done most of the experimental work, to study a simple system that we could address, we thought, equally well, both on the experimental side and on the computational side. So we decided to focus on a system in which interfaces are relatively controllable. So we looked into graphite, and the electrolyte that we're looking at, that we are considering, is an ACl in water solution, which is a system that in the nucleation community has been studied a lot. There is a number of force fields, for example, that are well characterized, and there is some expectation on how this system should behave in simulations. So in order to try and address the larger problem of understanding how surfaces control nucleation for this type of system, we have decided essentially to break down our problem into three parts. First of all, we wanted to be able to characterize what homogeneous nucleation looks like for an NaCl in bulk solution. And then we wanted to try and understand what is the effect of graphite interfaces on the solution structure itself. And then we hope, this is very much a work in progress, and we are combining these ideas and the results that I will discuss today in order to understand how surfaces, in particular graphite surfaces, can enhance the heterogeneous crystal nucleation of an NaCl. So I will start from a system that doesn't contain any crystal, and I will start from looking at the effect of graphite at the interface with the liquid solution that contains an NaCl. So here in this case, in order to be able to build a parallel between simulations and theory, and simulations and experiments, it's important to perform molecular simulations in realistic conditions. And in particular, here we use a technique that is essentially that we developed in order to be able to control the driving force of concentration-driven processes. Which is called the CMU-MD. It stands for Constant Chemical Potential Molecular Dynamics. So within this technique, what we are doing is essentially coupling a physical part of a system, which in our case contains an interface between a graphite electrode, a graphite surface, and a solution, with a reservoir. And then by introducing biasing forces, we are able to control the concentration in a simulated bulk for our system. So in this way, essentially, we are able to control the composition in the simulated bulk, and we're able to control the fact that our systems evolve under real electroneutral concentration background. So essentially, for our analysis, we focus on the physical part of our system, and we make sure that the composition in the solution bulk is always electroneutral. Essentially, that the bulk is always electroneutral. So the composition in terms of concentration of sodium ions and chloride ions is the same. The forces that allow us to impose these conditions are based on the application of, based on the calculation of densities on the fly and take advantage of Plume. So basically, here we use Gromax as an MD engine. The force fields that we employed have some internal consistency and have been used and tailored for this type of system in the literature. And again, a key part of this setup is played by Plume that allows us to essentially introduce these forces and control the composition of the system. So under this setup, being able to control the concentration in the bulk, we can study systematically how the interface behaves under different driving forces. So under the different configuration, under different concentrations. And what we start off by analyzing is the structure of the double layer for this type of system. So in this plot, basically, I'm showing the concentration profiles for sodium, chloride, and the oxygen and water as a function of the distance from a graphite surface. And you can see that the behavior of the system can qualitatively described by mean field Gouy-Chapman style theories. In the sense that if you consider that the absorbed layer, the peak of absorbed cation concentrations provide an effective surface charge, the concentration relaxation, for example, of the anion follows this exponential decay towards the solution. However, the comparison is qualitative, and especially by studying this type of structure, the solution structure at the interface as a function of concentration, we quickly realized that this type of picture does not hold for larger values of the concentration. So for example, if we move from 0.2, 0.3 molar to 1 molar, something interesting starts to happen. So basically here we have preferential absorption of sodium. So we still have a surface charge which is positive, but then there is a structuring process that takes place in the double layer. So we have an excess of counterions that follows, and then again a third peak in which sodium is again in excess. And then, of course, the two concentrations tend to electroneutrality in the solution bulk. And in this case, electroneutrality is obtained at a lower distance than in the previous one. So in this first set of simulations, we see that essentially the double layer shrinks, going from lower concentration to higher concentrations. However, these effects of structuring that take place at the interface and that are due to the fact that different ions have a different affinity for the graphite surface basically lead to further structuring as we increase the concentration. So here we go up from 1.2 molar to 9 molar. So essentially we go far into the metastable region for the system that we are looking into. And what happens is that we see that this structuring effect become more and more prominent. And in this case, we observe something different. So we observe that the double layer, so the length, the size of the double layer, so the length at which the two concentrations equalize themselves and electroneutrality is restored in the bulk of the solution, increases. So these two trends, A and B, where the double layer first shrinks as a function of concentration and then expand again, are actually not in agreement, disagree with the Debye theory, so with mean field theory that would expect this type of exponential decay for the size of the double layer as a function of concentration. However, they're consistent with recent experimental results for the same type of systems. And here, basically, we see that the double layer is behaving in a way that is highly non-ideal. And the presence of these structuring effects leads to an expansion for higher concentrations. Now, in order to validate the results, here we looked into the electrochemical properties of the double layer, exploiting this collaboration with the Warwick group that I mentioned at the beginning. So first of all, we look into how the structuring in the double layer leads to a screening. And here we are computing the screening factor, which goes to 1 when essentially the concentration of sodium and chloride equalize themselves, and exceeds 1 when we have an excess of charge for the ions that are absorbed preferentially at the interface. So we see that as we increase the concentration, here the color code goes from lower to higher concentrations, there is an overscreening effect that becomes more and more prominent. And then by essentially introducing the screening factor in an expression for the electric potential as a function of distance from our interface, we are able to compute how the potential changes as a function of our concentration. And when we compare this result with experimental results, essentially we see that the potential of zero charge that we are computing through this procedure actually has a trend as a function of concentration, which is very, very similar to what is observed in experiments. So here, for example, what we are plotting are results from simulations in blue and from experiment in black of how the potential of zero charge changes as a function of concentration. And what we see is exactly the same type of gradient for these regions. And then we also see a leveling off for higher concentrations. Now, the key difference here is that since we are running simulations that are very unlikely to observe to display any phase transition within the timescale that we're sampling, we can also expand the sampling and compute this type of properties for larger values of the concentration, while in experiments they're limited by the fact that at some point phase transition is triggered and this type of measurement cannot be done. So another comparison, which was very interesting, was based on computing, again, electrochemical properties in the presence of a charge. So we computed the capacitance for our system, finding very good agreement between experiments and theory. And then we computed the differential capacitance, which actually gave us a little bit of an insight in the limitations of our model, in the sense that here we are modeling a system, we are using a completely classical model, and we have absolutely no surface polarization. So what happens is that for a zero potential difference, we are getting large errors in the differential capacitance, while we get a very good agreement of this behavior of the differential capacitance for larger values of a potential difference on the electrode. And this can be explained actually by looking at the system as a series of capacitors, and essentially by considering the differential capacitance associated with the electrode itself, the contribution that is not coming from our simulations, we can actually back calculate it as a difference. And when we do that, we find again good agreement with the literature data. This is the differential capacitance for our electrode associated with the space capacitance of graphite, computed from our simulations, and this is a benchmark from the literature for a 6-layer graphene computed from DFT. So essentially, we are kind of satisfied ourselves that our description of the interface was qualitatively correct, and so we looked into what is the structural source of these non-idealities that lead into structure at the interface. And what we observe is that essentially there is an increase in coordination between sodium and chloride for higher densities close to the interface. In particular, between the cation and anion peaks, we see an increase in coordination. And when we perform cluster analysis on this type of system, we discover that essentially in this region, we have dynamically disordered ionic networks that are formed and that lead to the presence of clusters that are stationary characterizing the structure of the double layer. This has an effect also on the diffusion and the transport properties in the system. So here we're looking at the diffusion coefficient as a function of distance, which becomes slower than in the bulk as expected. And that also depends on concentration, of course. But structurally speaking, we observe this type of highly dynamic ionic networks that are localized in the double layer. And we see also that this type of structures emerge with increasing concentrations. And in particular here, there are these two trends that are shown to represent what happens in the double layer and how that is peculiar of the double layer. So basically, the square set of data shows how the number of clusters increases in the bulk of the solution. However, this increase in the number of clusters is not accompanied by an increase in the size of the clusters. However, in the double layer, when we increase concentration, what happens is that the number of clusters is accompanied also with an increase of the size of the largest cluster, which is indicating of these effects of structuring and formation of dense networks in the double layer. Okay, so how is this relevant for nucleation? We decided to look into, we think it's relevant in the sense that both computationally and experimentally, there are evidences of the importance of this type of disordered intermediate in the crystallization of an ACL. And in particular, there are computational results that show that beyond the limit of stability of the solution, the mechanism associated with nucleation of an ACL is two-step. These are results obtained with forward flux sampling from the Princeton group of Panagiotopoulos et al. And there's also some experimental evidence that suggests that disordered domains play a role. For example, there is a recent experimental result that shows that, for example, nucleation of an ACL in carbon nanotubes actually takes place through the formation of a disordered intermediate. And in this very nice paper, they were able to image directly the intermediate. However, in these cases, the process is taking place at a very high supersaturation. So in conditions that can be ascribed to something similar to the limit of, something similar to the experimental result, the computational results obtained by Panagiotopoulos et al. However, there are also other results that show this type of behavior appearing at lower values of supersaturation. So at lower values of the thermodynamic driving force for this type of problem. So basically, we set out to look a bit more in detail into the mechanism of an ACL nucleation within the metastable region. So below the limit of stability for our solution. And in order to do that, basically we have performed, first of all, unbiased simulations on the solution itself to try and characterize what the structure of the solution is in absence of any surface as a function of concentration. And what we see there is that, okay, we have dynamics slows down as expected, and a population of cluster emerges at the limit of solution stability. So whenever we have a metastable solution, we do not see a stable population of clusters. However, when we hit the spinodal, we do see the emergence of a stable population of clusters. This is expected, and this is in line with the existing results on this system. The type of structures that we see look a little bit like this one reported on the side, where basically these are kind of extended ionic networks with a core that is typically very dense. And here the atoms are colored with their local coordination number. So in order to try and study this process, we have decided to explicitly acknowledge the fact that in our system, we want to essentially expand the dimensionality of the reaction coordinate and go from a monodimensional reaction coordinate, which typically is considered when we look at nucleation in a classical sense, like this. We start from a metastable phase, we go to a stable crystalline phase, and the reaction coordinate is defined by the size of the largest cluster, indicated with N here. Basically, we wanted to expand this and explicitly acknowledge the fact that our clusters can actually grow both in size and in structure. So we decided to sample configurations in this space, in this two-dimensional space, where N represents the size of the cluster, and N of Q6, where Q6 is the order parameter we use to characterize order in a system, is the size of the order domain within the cluster. And in this space, actually, we have two limiting behavior. If we move along this horizontal line, we see essentially the nucleation of a one-step nucleation of an amorphous NSCI cluster. Instead, if we move along the diagonal, we have a one-step nucleation of a crystalline cluster. If we move somewhere in between, we have a multi-step process in which a system first grows in size, and then within that dense domain that is characterized by high local density, order emerges and a crystalline cluster is born. So in order to sample this space, we use metadynamics. And we use metadynamics in this sense mainly to generate input structures to then run unbiased simulations. So we noticed that, as you'll see in a second, essentially unbiased trajectories tended to concentrate in a subregion of this space. So we decided to use metadynamics in order to sample extensively this lower triangle and identify a suitable number of initial configurations for further studies performed using unbiased trajectories. So from this initial exploration, we move on to investigate the behavior and the pathway of these unbiased trajectories in this two-dimensional reaction coordinate. And we use a bunch of different techniques. The first thing we do is performing seeded simulations. So we perform simulations starting from an existing seed of different sizes. In this case, N, the size of the cluster, is something that scales with the radius of the cluster. So with the number of particles proportional to the number of particles elevated to the 1/3. And so basically you can see here some initial structures. And what we observe is that essentially the pathway that these trajectories collectively delineate in this two-dimensional space is indeed something that corresponds to a two-step type of mechanism. In fact, we start from the solution structure. The solution without any cluster is characterized by probability density in N, highlighted by this black line here. And instead, our process is moving away from this stable state, increases in size, and then a change in order is triggered. So in order to essentially sample also configurations that are away from this pathway that is generated by seeding, and basically we discretize this two-dimensional space and we perform a bunch of unbiased simulations within every discrete bin in this two-dimensional space. So the simulations here are between 40 and 100 per bin, and in this plot, what we represent is the average direction of the flux of configurations in this space. And you can see that essentially also this type of analysis highlights the fact that the preferred transition pathway from this state where there is no crystal to a state that includes a crystalline particle basically goes through this two-dimensional type of transition. In order to further analyze this type of unbiased simulations and be more quantitative in this analysis, we take all the unbiased data, which at this point is in excess of 20 microseconds, and we built a Markov state model with a reduced representation that looks like this. Essentially, we discretize this two-dimensional space into a number of discrete states and analyze this using the construction of a Markov state model. And this allows us essentially to further obtain insight in this type of process, in the sense that the total net flux projected over the discrete states also kind of suggests that there are more pathways, more than one pathway towards the formation of crystals in this state, but they all, I mean, the most probable one actually goes through a two-step process. So essentially involves once again an increase in density, an increase in size, sorry, for a dense crystal that is then followed by an increase in the crystalline order. And if we look at the committer projected on this set of discrete states, what we learn is that essentially we probably need to expand the definition of what a critical nucleus looks like in this type of system, in these metastable conditions. In this case, I mean, we're looking at a system that is highly supersaturated. However, it's not beyond the spinodal for this type of for this system. And however, basically, we see that clusters that are large, even if they're completely disordered, have a committer probability larger than 0.5. So essentially, clusters that are large but do not contain any embryo of the crystalline phase that will emerge for long times are more likely to commit to basin B, so to the formation of a crystal, than to go back and dissolve completely. And this kind of calls for an expansion of what we think of in terms of critical nucleus for this type of system, at least in this region of highly supersaturated solutions that are not yet beyond the spinodal point. Another thing we can do is also to estimate the nucleation rate for this type of systems. We do it from the slowest implied timescale for the Markov state model, and what we get is something very similar to simulations performed with other methods in these similar conditions. So we further analyze this process looking at the free energy surface obtained from a Markov state model, and we can see two reaction channels basically for this process. One that corresponds with this two-step process that I just described, and one that is more similar to a single-step process. And by performing large elastic band on this type of pathways, we see that the barrier for the two-step mechanism in this condition is likely lower. However, there can be competition between these two. I mean, the difference in the barrier is not very large. An interesting aspect of this type of analysis is that the clusters that are formed in this region, they do actually present an ordered core, which has a structure compatible with the macroscopic crystal, which is embedded in one of these extended ionic networks that are very similar to those that we see at the interface for much larger composition. So the main result for our interaction for the interface, the graphite interface that we studied and described earlier. So this brings me actually to my conclusions. And basically, we looked into how interfaces affect the structure of a solution, and then how local deviations from ideality in the structure of the solution actually play a role in the nucleation of crystalline domains of crystals for an ACL. And we see that basically basically the main message of these two pieces of the study is that these disordered clusters are an important intermediate in the nucleation in these conditions of high supersaturation. However, at much lower supersaturations, when an interface is present, seems to be able to catalyze the formation of these intermediates. And we are arguing, and now we are actively investigating the fact that the presence of an interface might actually lead to a change in the mechanism and lead to a speed up in the nucleation, not just by a decrease in the surface tension, which is the typical way these type of effects are rationalized, but also by actively changing the mechanism of the nucleation pathway. So thank you for your attention. I would like to thank all involved in this study, in particular experimental collaborator, Aaron, again, for the excellent work. All the details of these results are described in these two papers, and there are also input files and code available to reproduce them. So thanks for your attention, and yeah.
Thank you, Matteo. Great talk. I think Taro Karmukar wants to ask that did you try only Q6? I guess the local one to nucleate NaCl using metadynamics? If yes, what was your observations?
Yeah, so actually what we tried to do in metadynamic simulation was not to use an order parameter to bias our trajectories, but to only use a local density order parameter. So what we're doing what we're using as an order parameter for nucleation, for metadynamic simulations of nucleation, is the number of ions that has a number of neighbors larger than a certain threshold. So something that has to do with the local density of the environment. We enhance these fluctuations in local density, and then we monitor the evolution of the system, including a notion of order. We did that because we wanted to, most of all, to explore this two-dimensional space and generate configurations to then seed unbiased simulations. But for example, this limits a lot the ability to converge the free energy efficiently with metadynamics. So I agree with Tarak with the fact that if one wants to converge a free energy accurately using metadynamics in this two-dimensional space, both variables need to be driven probably, and in that case, one could use either Q6 or other measures of local order.
Okay, so
I think may I ask a quick one?
Yeah, Tarak, go ahead.
I'll take a couple of minutes. Ciao, Matteo. I just wanted to ask you something about the mechanism of this NaCl nucleation as a function of, let's say, the concentration. Do you see a similar kind of mechanism across a range of concentration, let's say binodal, spinodal?
So beyond the spinodal, this was very nicely demonstrated by the Panagiotopoulos.
Below. I'm talking about below.
Below the spinodal, we have focused at, basically we have studied this concentration, which is 3.5, S is 3.5, around 3.5, which is supersaturated. Supersaturation is large, but it's not quite the spinodal one. This study we've done only at that that concentration. There is a number. There are a number of results at the lower composition that suggest that the classical pathway is actually totally valid. The seeding results are very convincing in that. And so basically, what we are thinking is that first of all, there is a transition between the two pathways at a concentration that is lower than the spinodal. And the second thing is that this kind of highlights the role of these disordered intermediates. And I think what we are taking out of this result is the fact that when you have an interface, essentially, you are catalyzing the formation of this important intermediate and increasing the probability of going through this two-step pathway rather than just decreasing surface tension and enhancing nucleation through that.
True. Yeah.
Okay. So,
okay,
Christoph,
yeah.
Go ahead.
I said thanks.
Christoph?
Okay.
Sorry, thank you. Very nice talk, Matteo. So I was wondering, during the ordering, once you have formed this dense cluster and it starts to order, in some of your graphs, it looked like it bends back. So, which would mean that as the cluster orders, it shrinks. So is this something that you observe, or is this maybe just due to the
we have so quantitatively we have not characterized it, but we have anecdotally observed it in more than one trajectory. So what your observation is correct. It happens. We are thinking about what's really happening there, because it is as if the ordered core is consuming atoms from the disordered core in which it is embedded, but then the disordered core cannot keep up. So the addition of ions to the overall cluster happens at a slower rate than the rate of consumption of those disordered ions that are part of the cluster. So we are looking into this, and this kind of connects to the cashier theories around this two-step nucleation that, I mean, kind of inspired us also to use and describe the two-dimensional reaction coordinate space in this way. But we haven't done it quantitatively so far.
Okay, thanks a lot. But the other question is, so did you look at where the cluster starts to order and how it orders them?
So it seems to start from the core. How I cannot really tell. I mean, I don't have a convincing quantitative way of describing that.
Okay, thank you very much.
Okay. So Prabhakar, you want to ask directly, or should I read? Prabhakar. Okay, Prabhakar said, if I remember correctly, two-step mechanism for crystallization usually have the dense disordered phase resulting from the first step. Any comment? Yeah,
that's correct. In fact, I mean, in this case, you have fluctuation in density that form a dense cluster, which is not ordered, and then within that dense cluster, there is a formation of an ordered domain. So yes, it's what we observe.
Okay, so I'll take the last question from Amish Patel. Go ahead.
Hey, Matteo, very nice. So I have a bit of a technical question. So I really enjoyed and appreciate the importance of concentration fluctuations in the nucleation pathways. My question has more to do with the CMU-MD method. And I was wondering if, in addition to getting the concentration in the bulk right, does it also get the fluctuations in concentration that are consistent with mu-VT ensemble?
So at this point, it does not. At this point, the fluctuations can be tuned by tuning the strength of the harmonic force that is added to introduce this. So if one wants to tune fluctuations, it can be done, but it has to be done empirically by tuning the value of K. It is an interesting direction to potentially develop it in such a way that it could rescale directly, obtaining also the correct fluctuations. But at the moment, it's not like that. It's simply the average is simply obtained as an observable.
Thank you.
Okay, thank you, Matteo. So our next speaker is Professor Peter Bolois. He's a professor in the Van Top Institute for Molecular Science at the University of Amsterdam. His research topic includes transition path sampling methods, kinetic folding pathways of small proteins, and nucleation of methane hydrate, to name a few. Today, he will talk about improving molecular models through path reweighting methods that constrain kinetic observables. Peter, go ahead.
Hello, am I visible as well?
Yeah. Right. You can hear and slides are visible, yes.
Okay, very good. Okay, thank you very much for a kind introduction. I also like to thank all the organizers for giving me the opportunity to present recent work here at a RARE meeting. I've been to the previous RARE meetings as well, and I really enjoyed them, I have to say that. And I hope the next meeting in a couple of years will be really on site in India. So without further ado, I would like to start. And I'm going to talk about biomolecules and about, and in particular, we know that biomolecular structures experimentally follow from X-ray diffraction or NMR or cryo-EM nowadays. And at the same time, we can extract thermodynamic and kinetic information from, for example, spectroscopy. Now, as theoreticians and simulators, we like to actually do or make predictions of static and dynamic properties at the atomistic resolution using classical MD. But we normally think of that this is pretty accurate, but there are in fact two sources of error. And this is, of course, the sampling error, which is probably the subject of most of the contributions to this conference. But I'm going to assume that this is solved for the moment. I'm going to focus on the second source of error, which is the systematic force field error. Now, it is possible to combine molecular dynamic simulations with experimental ensemble measurements to compensate for force field errors. And this has been pioneered, amongst others, by Michele Vendroscolo's group and also Giovanni Bussi's group and I think many others. And a rigorous framework for this strategy is the maximum entropy principle, or short max-end. Now, just to be clear, max-end states that the best probability distribution, P of x, for a certain state x that is compatible with the observed data is the distribution that maximizes the Shannon entropy, or also known as the maximum relative entropy, or also known as the Kullback-Leibler divergence, and we actually denote it over here as this function, and it compares two distribution px and a prior p0x. And what you can do now is actually maximize this function under, so you actually vary the distribution, the target distribution, such that this is maximized under certain constraints, namely that some observable SI, the average of that, the ensemble average, is then constrained by some experimental data. So this is the second line here. So you can actually do that for multiple ensemble averages simultaneously. And of course, the third line is a normalization condition. Now, if you want to solve this, you don't want to do this just like that. I mean, there is a nice method to do this. This is called the method of Lagrange multipliers, and I think you all are familiar with that. You can actually define a Lagrange function by adding these constraints, and then solve this by just taking the derivative and set this to 0. And then you end up with a general solution where the maximum entropy target distribution is reweighted from the prior distribution. So this is your prior distribution here by a reweighting factor, which contains the observable itself, S of x, and a Lagrange multiplier. Now, this is very akin to Legendre transform, as you probably know. Now, how is this working in practice or in an example? This comes from this nice paper here. If you have an order parameter S or an observable S, and you measure some distribution this is the purple distribution, this is then your prior, which has an average along this gray line. But of course, it doesn't fit completely with the experimental S, which is the red line. Then you can actually apply this framework to reweight this distribution. And this is what happens here, so that these averages are the same. And now, of course, also the free energy has shifted and all the populations have shifted. So you can actually correct for measurement errors or for systematic errors in this particular way, for example, for free energies and other thermodynamic quantities. Now, this is all very nice, but we all know that the next step in the system determination, or what we also want to do, is to think of dynamics, of kinetics, and we want to include interconversion rates. Now, of course, we all know that MD can, in principle, also do kinetics. It can construct a kinetic network. For example, you can develop a Markov state model, but this can go wrong because, for example, force fields are not completely accurate for this. They are not optimized for this. So here we provide a method that actually combines MD with these experimental information using maximum entropy approaches for trajectories. Now, this is just some illustrations for Markov state modeling. Now, how do we do that? So we want to incorporate the experimental data. So if you actually think of that current force fields were not optimized for kinetics, and you want to incorporate this, the obvious strategy is to modify the force field a little bit, recompute the kinetics and compare it to experiments, and then do some learning and optimize. Now, this is, of course, very problematic because the recomputing kinetics can be extremely expensive. Just doing the first step is already very expensive. So a better option would be to reuse existing trajectory data and correct for some errors. Now, you can take, obviously, the cue from max-end, from the maximum entropy principle, and we put an experimental constraint on the path distributions. That's the idea. Now, of course, then we need to define what a path is in the first place. We actually use a very simplistic approach. A path probability is a function of a high-dimensional vector, where x is just a sequence of states. The initial distribution is given by, rho of x, and then you have a product of short-term Markovian propagators that actually brings you from one state to the other through space-time. So these are space-time polymers, as David Jana likes to say. All right, so we're going to apply now the equivalent of max-end, which is the maximum caliber approach. And this was pioneered or introduced even by James in 1980, which is a variational path-based framework that is used in statistical mechanics. Up to now, it has been mostly used in discrete systems. For example, Ken Dill and co-workers have written quite a few reviews on this, and also other people like Patrouche has used it in his methods. We are using the continuum version of this. The path entropy is a very similar looking cubic Leibler divergence. And we actually are going to do exactly what we did in max-end. We optimize the path distribution P of x under the condition or subject to that the path average that we do the observable of is equal to an experimentally observed kinetic variable. Now, this could obviously be the rate constant. Now, standard maximization then gives exactly a similar, or exactly the same, or very similar expression where we have a prior path ensemble and we reweight this path ensemble with some exponential prefactor, where this exponential prefactor has now the path variable, the observable as a function of the path. Now, this looks indeed very similar to max-end, but depends on the path x itself. Note that it also has similarity to what's called tilting of path ensembles, and in particular the S ensemble that is also pioneered by several people in the community. I refer to this paper by David and others. This is actually a very powerful approach. Okay, so just to recap, I mean, if you have a maximum entropy principle, then you can actually take configurations and you have a prior distribution, which is obviously a little bit wrong, and then you can move it to the right observed average by reweighting. And we can do something similar for paths, but of course that then you have a path ensemble. Now, the question is, of course, how do you get path ensembles for rare events? That is a big challenge. And that is where enhanced sampling, and in particular path sampling, and in more particular even transition interface sampling comes into play. So suppose we want to study a two-state system where we have an infinitely long trajectory. In principle, of course, in practice, this is very hard. What we want is to create a staged sampling algorithm. So we introduce a set of interfaces which foliates the space between A and B. And then we focus on the paths that actually leave A, for example, cross a certain interface and then come back or go on to B. And suppose that we actually focus on the green one. This is the lambda ith interface. We can actually now sample all the pathways that go through this interface and cross this particular one. This one cannot, so this is rejected. And then you can compute the probability that a path this is crossing this particular interface for the first time after leaving A can also cross the next interface, or actually even go on to B. That's the crossing probability. And we can then construct the rate from this by just a product of all these interface crossing probabilities. We actually need another factor called the flux, but this is easy to construct or even to measure. Now, note that this is an exact expression, so it yields exact rates independent on how you choose lambda. And by coincidence, this is also actually not so coincident. This is also the basis for the forward flux methodology. Now, we can actually reweight all these paths using the WHAM approach, weighted histogram analysis, to actually construct a complete path ensemble of the system. Now, as an intermezzo, I'm going to show you a couple of examples. So here is some trip cage folding we did quite a long time ago. Here's some more recent work. There is the DNA base pair rotation, which actually can be studied with this type of approaches. So here we can predict forward and backward rates and compare them to experimental work. And more recently, we looked at methane hydride nucleation. So this actually fits very well with the previous talk and probably also with Sapna's work on the first day. So we can actually apply TIS efficiently using open path sampling and then compute the crossing probabilities and hence the rates. Now, if you have the rates, that is fine. You can compare to experiments, but you can even do more, of course, and you can use the trajectories that you have sampled, which actually are unbiased sampling, unbiased MD, to interpret the reaction coordinate. And this is something that we have explored quite a bit. And very recently, we ventured into some machine learning algorithms to do so. So we actually computed committer data from the reweighted path ensemble. And we used a new, well, at least an autoencoder approach, which we call the extended autoencoder, because we use the features from the simulation to feed into the neural network. And of course, the autoencoder tries to reproduce this, and it goes via a bottleneck where the latent space, this is called the latent space, but this bottleneck is also used to predict a committer itself. So the committer value is predicted. So this is a combination of a committer prediction and a dimension reduction at the same time. Now, using for simple systems, we can actually really recompute the committer exactly, and we can also get the latent space pathway out of this. But we also apply this to the nucleation data, and there from the raw ground truth that we can really predict the position of all the bottlenecks and the transition state ensembles. Then you can actually also construct the latent space path, and it looks like this in this radial polar plot. And using importance sensitivity analysis, you can also find out which are the most important features. Now, this is all very nice, but of course, as you all know, going through a latent space is still hard to interpret. I mean, what does it actually mean, this latent space? And therefore, we want to also have some human interpretable coordinates. And this is a plot that probably Garrett Hummer showed already 2 days ago. We teamed up with them to use their symbolic regression methods to make the mechanism more interpretable. And so my student Arjun actually applied this to the methane hydride formation and really could actually distill from the data a human interpretable committer function, which contains not only the size, but also the structure and the temperature as a parameter. So this was actually quite nice. Now, going back to the main topic of today's talk, so we want to apply what is now called continuum path ensemble MaxCal for a simple potential, just to show the proof of principle. So what I show you here is a two-dimensional potential. We do, and this is really simplistic compared to the complex systems that I showed 2 seconds ago. So this is one particle, so it's a two-dimensional particle, two-dimensional potential, doing stochastic dynamics on this, well, reasonably rough potential. So the TIS gives you then path ensembles, crossing probabilities. Joining these ensembles gives the total crossing probability and the rate. So here's the form of these crossing probabilities. And you can actually think of this as a projection of the full path ensemble, which is given here for all paths that leave A. And it's determined by measuring how far these trajectories go. So this lambda max is a function that measures how far paths go. And this is a very important feature, a very important function. It just measures the progress of the path, and if it goes to the full to the other states, then of course it goes to the end, and then lambda max is very large, but usually it does go back before it actually crosses the barrier. Now, I just should say that TIS also gives configurational density distributions and hence also free energy projections on arbitrary CVs, but this is a side remark. And if you're interested, you can look at this paper for more information. So how do we then continue? Because now, of course, we have some technical issues to resolve. So TIS gives expressions for the rate constants. So these are the ones that I just gave. And we can impose that using the Lagrange method of multipliers, or the method of Lagrange multipliers. And standard optimization then gives again a prior plus a reweighting factor. Now, this reweighting factor is a lot more complicated now because it actually, well, formally it's written like this, but it's an implicit function. It cannot be resolved just like that. In fact, it's not well defined. It's not fixed except at the endpoint. But there's a big but. We can use the projected configurational density, in other words, the free energy from the path ensembles to actually determine it. Now, how does this work? Well, first of all, you use the path ensembles, which are reweighted, and a instantaneous density operator to project on an order parameter. And then you should realize that this max-cal density should be, of course, identical to the density that you obtain from any max-end approach, which was the configurational approach. So if we have a similar expression for the configurational density, then you have to use, of course, a different function, which is now called G. But the question is, what is this G? Now you have to combine it or relate it to an experimentally known function or experimentally known observable, and that observable we found out is the equilibrium constant or the equilibrium fraction. Now, as you know, the equilibrium fraction can also be expressed in rate constants. This is just a simple form. And then we can take the ensemble average of this function, and that should be equal to this particular fraction. Now, if you do some rewriting, you can see that there's only one function that actually obeys it, and that function is the committer function PB. So we actually found out that PB is the function that we need to fix this unknown function f. So just to give you a simple illustration, so the max end reweighting for the density is this reweighting like this. You have a prior and a reweighting factor, which is determined by the imposed rates. You get a new density for both the A side and the B side, the forward and the backward reaction. And this gives you a corrected committer, which looks like this. This is a simple expression, of course. But if you now plug in these things, you see that this actually becomes an implicit function for the committer. So here's the committer and there's the committer. So you have to solve this numerically because this is not an analytically solvable function. But how this works is as follows. So you can have here a density function that in blue for A and in orange for B. So these are just proof of principle ideas of very simplistic functions, but of course there's a barrier in between, so this is very unlikely. But you can compute from this an analytical prior committer, which is the blue curve. And of course, using this equation, you can then calculate the orange curve. And from this orange committer, this new reweighted committer, you can then plugging it in here, you can get the densities. For example, if the densities are very simple over here, you can now have new densities. And from these new densities, using the max and posterior, we can then calculate this f function. Okay, so that's a very long, winded story, but it ends up that we actually, for this two-state potential, we can do this. So, for example, we start with a path ensemble that goes all the way back and forth, and then we say, this is not quite right. We need to correct the forward rate by about 1 kT. And if you then again do the prior committer, you get this red curve. Correcting it for the for this Lagrange multiplier gives you the black curve. It looks a little bit different. And then you can actually do the max end approach, which gives you this black curve in the bias function. From the bias function, you get a new bias function. This is the red curve. This red curve can then be used to reweight this prior density to get a new density and new crossing probabilities. And you can see from the crossing probabilities that these the new crossing probability is really nicely behaved and actually shows you that there is exactly 1 kT a lower probability in crossing. So the actual rate really decreases by e to the power -1, which is very nice. You can do even a more stronger correction, in this case in both directions. And what happens then is that your free energy here, so this is the prior free energy, is reweighted to get a completely new free energy, which actually is shifted and actually a little bit higher because, of course, the forward rate is decreased. And the crossing probabilities behave very nicely indeed. Okay, so I can imagine that this is a long story. And what have we actually done now? So it's good to interpret this method. And so we have now a maximum caliber-based method to reweight existing molecular dynamics trajectories from some path ensembles. And this can be from regular MD, from TIS, from FFS, or from any other adaptive scheme, as long as it is unbiased dynamics. And then we are reweighting these based on the progress along an order parameter. So in fact, the paths are made less or more probable in the path ensembles. And this is completely analogous to the maximum entropy approach. Now, the rate constants are automatically constrained to the correct value via this function. And we actually need this other bias function on the committer that to actually fix the entire function f that we actually use as a complete bias function. Now, this is showing this in cartoons again. So here is a barrier. We have a bunch of paths. And you can see that the blue path only comes up half the barrier. This path comes up to the complete barrier, but then recrosses. And you get, because of this function, this bias function measures how far the path comes. And this actually determines then this bias function. So this gets a different bias than this one. And for example, it gets a higher weight or a lower weight, depending on if you want to enhance the rate or suppress it. So that is actually the interpretation. Just a final example is now for protein folding. So here is Chingling folding. We took the input data from a straightforward trajectory. It shows you how you can use this. So we actually have some data from the show. And then the theoretical or the predicted rates at the melting temperature are these numbers. But if it is at the melting temperature, they should be obviously the same. So clearly there is a mismatch, and this mismatch is due to the force field. This is, of course, the assumption. Now, what we can now do is correct the force field by a folding rate and putting it also to the unfolding rate. So we lowered the folding rate. Now, we can also do it the other way around, but we chose to do this. Now, then you can do the whole the framework. So I don't go through all these things, but I mean, as you can see, the free energy barrier at the end as a function of the native content fraction Q is slightly increasing, and actually the barrier also increases. So this is the effect of the correction, and it's actually really a qualitatively different curve. You can actually also look at it in terms of two-dimensional free energies. where you have here the original data. Here's the transition state. So this is the solvent accessible surface, and here is the Q. And in the reweighted paths, it's shifted. And also in the committer surfaces, it is shifted. And if you then look at the configurations, because of course you have all the paths, and we can actually identify now the transition state, and it has qualitatively changed. It goes from 1 hydrogen bond to 2 hydrogen bonds. So you really do a new discovery by really reweighting these paths. Okay, I want to end up with concluding that we actually, presented here a new general method that imposes experimental dynamic constraints with Maxwell. It can impose rate constants and at the same time yields consistent free energy projections. Important is that it is a post-processing method. It doesn't need costly re-evaluation of path ensembles, and it reveals some changes in transition states. And I think it's applicable to many different approaches, many different systems in biology, physics, chemistry, and material science. Now, as an outlook, we have independence from CV. From a CV definition. I mean, because we, of course, we still use a lambda to see how far the path went, and we would really like to be independent on that. Another outlook is that this is all very nice, of course, but it doesn't change the paths. The paths are in fact not altered. And what we would like to do is to come up with a method to improve a force field, and especially all atom force fields with this method. And one way to do that is, and this is the last slide, it's towards a force field optimization for kinetics, where we use a simple concept. We just, instead of optimizing with respect to the entire distribution, we now use an optimization with respect to some order parameters, sorry, not order parameters, force field parameters. I'm laying out very quickly how you can do that. So there's a Lagrange function again. So this is the Kubert-Leibler, here's the constraints. And then we actually use a concept which was introduced by Bettina Keller yesterday, where we actually use a reweighting factor for going to the prior to the posterior. And for example, for the over-den Langevin, we can use the Onsager-Machlup type of action. And then you can crank the handle and do calculate this. And this is also what Bettina showed you the day before yesterday. You can compute all of this and then optimize this Lagrange function to optimize the parameters. And just as a first step, we actually looked at the at the rate constant derivative. So here's the rate constant for the constraint, and it actually works quite well for comparing an action derivative and the numerical derivative of the rate, which is actually quite nice. And this is, of course, ongoing work. And next time, I hope to tell you a little bit more. I will end with some acknowledgements. Let me see. Most of the work has been done in collaboration with Michele and Faden. But of course, I also presented some work by Arjun and Martin. And of course, I need to thank David Swenson for his OPS development and Josephine Frede for collaborating with the DNA work. I just want to point out that there is a postdoc and a tenure track position available in our institutes. And here's a nice picture of the group in happier pre-COVID times. So I'll leave you here and ready to take some questions. Thank you.
Yeah, thank you, Peter. There are a few questions in the chat box. I'll just go that first. Shravani Tarabdar asks that how well can you generalize this copy max scale to the cases where you have multiple degenerate starting and ending states?
Okay. So the question is that I presented it for a two-state system, and the question is, can you actually do it to a multiple state system? That's, I think, the question. And the answer is yes, this is possible. Just as you can also do multiple transition state sampling or transition interface sampling. You can also look at the transitions from each metastable state to each other metastable state and do the reweighting for the separate path ensembles. This is perfectly possible. In fact, in our review in the European Journal of Physics, if I'm not mistaken, there is a treatment of that.
Okay. So next one is Satyabrata. He's asking that, can you please explain how we can design the loss function in extended autoencoders such that along the latent space, we can ensure to get the commuter instead of something else?
Okay, this is probably a very difficult question to answer.
Yeah, I also find so.
Let me just say, I mean, I can say something that the loss function is indeed, I'm going to stop sharing for a second because I want to read the, yeah, the loss function is indeed a tricky part. So what we did was we take the loss function of the committer. We try to reproduce the committer with the predicted one and the the true one, of course. So that is what we did, but of course it depends whether or not you take the committer itself, the logarithm of the committer, the binary logarithm function, and I mean there's a lot of different loss function constructions that you can try, and we found out that the if I'm not saying the binary logarithm is I think the best one. And I'm not sure if that answers the question, but otherwise I'm happy to talk about it afterwards.
Sure. So Andrew, you can go first, and then I think Pratyush, you can also ask in person.
Talk, Peter. I really enjoyed that. And also brought back nice memories of RARE 2017 when we were hanging out together in Agra. So hopefully, yeah, like you say, we can do this in person again in the future. So my question was on uncertainty quantification. So like you nicely pointed out at the end, you're reweighting sort of the ensemble that you currently have into sort of, you're taking your current paths and reweighting them. And so I suppose if you push it too hard, you may have very few paths that are representative of sort of the new constrained ensemble. And I was wondering if there's a way of quantifying sort of what uncertainty you might expect given how much you're driving it, depend on sort of the Lagrangian term.
Yeah, I think there are several things here. So as you said, indeed, uncertainty quantification is important. And in particular, for example, how do we take into account the fact that also the experimental data is maybe not completely accurate. There's maybe an error bar on that. It's possible to add this error in the Lagrangian approach. So you just have some sort of a confidence variable. So you have a variable that tweaks the confidence in your data. And then you can go from a completely constrained, which is infinitely confidence, to a completely unconstrained penalty function, let's call it that. And of course, that's by tuning this, you can actually go from not biasing at all to a complete bias or a constrained bias. And in this way, you can say something about how the reweighting reacts to this particular variable. But talking about the other thing that you mentioned, that a few paths might dominate, this is this is something that you really should probably check, because the method works such that all paths, and the way that they're presented now, the method works that all paths that reach a certain point in this lambda space or in the CV, they are reweighted with the same weighting function. That's because we constructed that way. By construction, this is the way it's happening. So all of these paths that end at that particular point, they get the same weight. And depending on how many you have, that's also depending, that's also answering your question, basically. So you can really look at this biasing function, the F function, to see whether or not this goes right or wrong. So of course, if you have a divergence in your biasing function, an infinite peak, obviously something is wrong. So this is, And another point is to make is that we didn't really look into error analysis. I mean, obviously we need to do things like bootstrapping, just block averaging, and all the standard tricks that we need to do to check these the sensitivities of these methods.
Okay, so Pratus.
Yeah, Peter, great talk. I had a question about using the max-cal expressions for rate. So most of the times they end up assuming Markovianity when they write down the max-cal rates. When you are using the expression. So are you assuming Markovianity along your paths? And that connects to the other question. If so, then you do have to worry a little bit about the collective variables.
Yeah. Good question. Very nice. You're right, of course. If we have to worry about Markovianity for the transitions, or for then we have to be careful. The way that I presented it was using the TIS framework, and there I think we can safely say that there's no Markovianity assumption in that framework. And so the rates are really constructed from these crossing probabilities, and they are non-Markovian. That means that it has the entire history of the path in it. So it's not only dependent on your previous interface, for example. And so that's an important point. However, the state definition itself and the state-to-state rates, they are Markovian, and that is a big assumption. So we assume that if you go from A to B, you lose completely your memory of A, and then you re-equilibrate in B before you go back to A or to another state further down the road. So this is of course always the case with any Markov model or Markovian model. You have to be careful how you define your states. And but if this is well done, if the states are defined in a good way, and I mean, for example, for nucleation, this is of course, well, it's not trivial, but it's very clear that you can distinguish these. For a protein, it's harder, of course, and we all know that. But on the other hand, yeah, we are pretty confident that folding and unfolding can also be distinguished, although sometimes it's difficult. We know that. But this is a good point to
okay,
think about.
So thank you, Peter, for this nice talk and nice discussion also. We're lagging behind a little bit, so I will just have a 5 minutes break and then we'll come back. Is that fine?
I'm fine with it. So thanks very much.
Okay.
Looking forward to...
Okay, so as I have officially said that it is a break, I'll just ask something to Peter in the break. So when you are doing this duetting thing with your kinetic parameter at a particular temperature, like the last one you said that at a particular temperature, you have these differences in Ku and Kf, I guess, for the folding of the small peptide. And then you correct for this. So is it transferable? That means...
Yeah, very good question. So this is something that we haven't looked into. I mean, my gut feeling is that for a different temperature, you have to redo the rate calculations. And it's not completely clear to me whether or not the reweighting factors or the reweighting biasing functions will change. And this is actually, we didn't explore that. So, I mean, that's something to look into it.
So you mean the different temperature, I have to correct the rate to produce something at that temperature?
Yeah, so this is actually, so this is what we do often in biomolecular simulation, that we just fix the temperature and then we don't touch it anymore. This is what, because one temperature is already very difficult to do. And except for if you do replica exchange or something. But if you do multiple transitions or multiple temperatures, you can possibly see how this framework changes over the temperature range. But it is, we haven't done that. I mean, it would be really nice to do so actually.
Thank you.
All right. So well, I guess that I need to now. I can just stop my video, or at least my microphone.
Christoph, would you like to share your screen just to check?
Did you talk to me?
Yeah. Would you like to share your screen?
Yes, I can try to do that. Let's see.
Good morning. After you do that, I'd also like to try and share my screen, make sure that a sound from a movie can go through.
Does it work?
Yes.
Yeah, it's great.
Yeah, yours is working. Yeah. Can you unshare? Yanis can share.
Yes.
Yeah,
Okay.
let me try that. Okay.
Yes. Can you?
You know, the screen is
Slideshow
through.
mode,
Now
or?
let me find the movie. So here's the movie. And I want to, if I go in, I want to make sure that, okay, so more share sound. Okay. So I share the sound. Let's make sure that it's not horribly loud.
That's working.
Yeah, it works.
Okay, good.
Pretty good, yeah.
So I'm stopping sharing.
Yes, thank you.
Okay, so welcome back. Our next speaker is Professor Christoph Telago. He's currently a professor and director of the Erwin Schrödinger Institute for Mathematics and Physics at the University of Vienna. He works on the general area of computational statistical mechanics, which includes rare event simulations, machine learning for molecular simulations, phase transitions and nucleation processes, stochastic thermodynamics, and nanomaterials. Title of his talk is Fluctuating Interfaces and the Bulk Melting of Ice. Christoph.
Thank you very much for the introduction. And of course, thank you very much for including me in this very nice conference, which I have enjoyed very much so far. Of course, it's not like the other one that we had some time ago. I'm talking about the 2017 RARE meeting that we had in Agra. That was really really nice, but very good that you are organizing this meeting online here, particularly because the next time around we can then talk about this meeting we have now, and we will say how much better it is to meet in person than online. But this is the best we can do now, and I'm very happy to be part of it. So thanks for having me. Today I'm going to talk about a little thing that we did, that I did with some people in my group, and with also with Phil Geisler from UC Berkeley. So the work that I'm going to talk about is mainly the work of Clemens Moritz, a doctoral student in my group, and of Maxina Bichler, also a student in my group, and of Marcello Sega, who is now at the Helmholtz Institute in Nuremberg, and also Philipp Geisler contributed. Actually, this was something that we started when Phil was here in Vienna for a sabbatical. If you're interested in what I'm going to tell you, you can, it's all in these two, sorry, I should go to full screen. It's all in these two articles. Now, what I will be talking about is a problem that came up when we studied how ice melts, how water ice melts, and but in particular, how it melts in computer simulations with periodic boundary conditions. Turns out that a question that comes up is that of fluctuating interfaces, fluctuating and diffusing interfaces, and it's then relevant to know at which distance the two interfaces touch. Now, so this is the main question that I'm going to answer, and then we'll see how that is relevant for understanding how ice melts. Now, it's known that melting is actually a process that starts at the surface. In the case of ice, we know that ice, even below the freezing temperature, is covered with a liquid layer of water. And this is an observation that was first made by Michael Faraday in the 1800s. Faraday made his famous regelation experiment, where he found out that if you put two pieces of ice together, they freeze together, forming one block of ice. And his explanation was that the ice is covered with a liquid layer, and when this liquid layer that is then put into contact with another piece of ice, then you have ice on both sides of this liquid layer, and the liquid layer freezes. This liquid layer is actually the reason why you can make snowballs, why they stick together. Now, the thickness of this liquid layer grows as you approach the melting point, as it's shown in these very nice results of David Limmer and David Chandler. And since you have this liquid layer on top of the ice, there is no barrier for melting, and the melting just proceeds from the surface into the bulk. But this is not always the case. There are cases where the melting actually occurs in the bulk, and the first to study this was John Tyndall, actually the successor of Michael Faraday. How he did it was that he took a block of ice and he focused sunlight into the ice, and at the focus, the sunlight heated the ice above the melting. And if that happens, the ice melts at that point, and it forms so-called Tyndall figures. You see some of them here drawn by Tyndall himself. They have these very nice dendritic shapes. The particular shape is due to how surfaces grow in ice and how heat is actually transported. Here on the left, you see some more recent figure of a Tyndall figure. What's also interesting is that here at the center you have a bubble of vapor. Since the liquid actually has a higher density than the solid, immediately when you form a cavity filled with the liquid, you have negative pressure, and in this negative pressure, a vapor bubble forms. You have cavitation. So there are also other ways to observe melting in the bulk. For instance, if you take a silver nanocrystal and you cover it with gold, which is a higher melting point, then the silver crystal does not melt from the surface, but in the interior. Now, how does this melting occur? Actually, if you want to know how melting in the bulk happens, you have to apply special sampling techniques, and this is actually one of the main topics of this conference. Bulk melting is an activated event because it proceeds via nucleation and growth, and therefore free energy barrier has to be crossed, and therefore the melting is a rare event. So a number of people have studied how melting occurs in the bulk. For instance, in this very nice work of Mark Tuckerman and collaborators, they studied how copper melts by applying adiabatic free energy dynamics and the string method, and they found that there are multiple competing pathways that connect the solid, and here A is the solid with the perfect solid and the solid with a few point effects, and in B here they cluster, and then there is a transition to the liquid. You can go to the liquid via a number of different pathways, and all these pathways involve some defects. Similarly, the melting of ice was studied by Donadillo, RARE2021 and Painello using metadynamics, and what they found is that the transition between the stable states representing the solid and the liquid proceeds via the formation of so-called topologically 5+7 defects. We will hear more about these defects later. Now, if you would like to study dynamical pathways that do these transitions, what you could do is to start them at the transition state and let the system go. But of course, here, as in many other cases, you don't know where the transition state is, and therefore we have all these powerful methods that allow you to study the dynamics of rare events, mechanisms, and rates. Now, but there are cases where you know where the transition state is, and one example is, maybe it's a bit artificial, but one example is the example of melting or freezing at coexistence. So why do you know the transition state in this case? Imagine that you have a system that is at coexistence, and what's shown here is the free energy of the system as a function of an order parameter that quantifies how much of the system is present in, let's say, the liquid phase, and how much of the system is present in the solid phase. Now, if you go from left to right, you go from the liquid to the solid, and the red curve here shows the shows the free energy profile as a function of this order parameter. This could be, for instance, be the number of molecules that sit in a crystalline environment, so that a large value corresponds to the crystal and a small value corresponds to the liquid. Now, if you go, as you go from the liquid to the solid, the free energy goes up and then reaches a maximum, and then it is flat for quite a while. And this flatness here corresponds to the formation. This flat part here of the free energy profile corresponds to the formation of a slab, where some part of the system is liquid and another part is solid, and they are separated by one, or actually by two, flat parallel interfaces. Now, changing the amount of solid compared to the amount of liquid is something that does not cost you any free energy at coexistence, because you don't change the size of the interface, only the proportion of liquid and solid. And since they have the same chemical potential, the free energy profile is flat here. And the height of this free energy barrier is related to the surface free energy. Now, in this particular case, the transition state is known because it corresponds to the slab. It's somewhere here in this region, and in order to produce a trajectory that goes from the liquid to the solid, what you could do in this particular case, because you know the transition state, is to prepare a slab and then let the system go from the slab. Of course, away from coexistence, the situation is different. Away from coexistence, your free energy profile as a function of this order parameter would look like the blue curve here. And here, even in the case where you have a slab, you have a thermodynamic driving force towards the liquid state, and the system would slide down here very quickly, starting from the slab always to the liquid state. The transition state is somewhere else, and in general, you don't know where it is. But if you have a system at coexistence with periodic boundary conditions, you know that the transition state is actually the slab. So you could, in principle, let the system go from the slab, and this is what you would observe. So here, this is a trajectory where we started in the slab, and this trajectory here happened to melt. The blue particles here are the blue oxygens are oxygens of water molecules that belong to the crystalline phase, and the red ones, they belong to the liquid phase. Now, in other cases, the system will freeze. You see, you have these interfaces, the two interfaces that grow here, and they grow in a way such that the liquid part shrinks. And if you wait long enough, you will end up with the perfect solid. Actually, this solid that we have obtained here is not quite perfect, because a defect is remaining here, and this is a 5+7 defect that we're going to talk about, later. But I would like to answer the question now, to address the question, what can we learn from studying melting or freezing at coexistence. What can we learn by studying this process about the process occurring away from coexistence? Does it have anything to do with what happens if I go into the if I make one of the two states metastable, if I really go away from coexistence? We know that at coexistence, actually nothing should happen because the nucleation barrier will be infinitely high. But in a finite system with periodic boundary conditions, the barrier is not infinite and nucleation can occur. But the question is, so what does this nucleation have to do with the nucleation that happens away from coexistence? Let's have a look at this for a simple system, namely for the Ising model in 2D. And the Ising model at 2D without an external field can have a transition from a spin down state to a spin up state. And during this transition, an interface has to be crossed. And how it is crossed, you can see here. So this is a, you can see here that this, let's watch it again. Let's start from the beginning. You see that you have a cluster here, the cluster grows, and it grows laterally. It grows in an elongated way until this cluster touches itself across the periodic boundary condition, and then you have this slab, and the slab grows, and it grows slowly because this growth is diffusive, and once it has grown, once it has grown enough, let's speed this up a little bit, then it will actually go down on the other side of the barrier into the other phase. Here on the right, you can see the trajectory in a space spanned by two order parameters. One is the magnetization. So this magnetization tells you that we go from the spin down to the spin up, to the spin up state. And this parameter D tells us something about the geometry of the cluster that forms. Actually, for positive values, it's the difference, it's the shortest distance of the largest cluster to its closest periodic image. And once a slab has formed, it's the thickness of the slab at its thinnest position. So this is what happens at coexistence. Away from coexistence, so for the Ising model, this would correspond to a situation where you have a field. Something similar happens, but not quite, because you have a cluster that grows. The cluster is spherical, it's much more compact, and then it touches its periodic boundary, and then very quickly it goes into the other stable state. So you have a slab again, and the slab forms and grows, but it forms in a different way when you go away from coexistence. You can see that more clearly here. So without magnetic field, you have this elongated cluster that forms the slab, and it grows until the slab breaks. And with the magnetic field, the cluster stays spherical until it touches, and then it forms the slab much more quickly. So if at all, only the initial stages of this process are comparable in the two cases. Really, the early stages of the nucleation, where you have these small clusters that form, are comparable, but what happens after that is clearly different, and it's a consequence of the periodic boundary conditions that we use here. So what is the limit of size for which you may expect that the two processes are related, are similar? Well, it's the thickness. Imagine the process in the reverse direction. So the size of the cluster is equal to the thickness of the slab when it breaks. And this is the size that is an upper limit for the size of the nucleus at which it still can resemble, can be meaningful for the transition happening away from coexistence. So, and this is the thing that I would like to talk about now. Namely, imagine that you have this slab, and this slab has two interfaces, and these interfaces fluctuate. At some point, the slab breaks, and I would like to understand at which distance this happens, at which slab thickness the slab is likely to break. So let's state this problem more clearly. Imagine that we have two interfaces. The interfaces have average positions, and the distance between the average positions is x. These interfaces, they also fluctuate. And if a fluctuation occurs that is large enough, for instance, here it might occur soon if this interface, this thickness here shrinks even more, then the two interfaces might touch each other. So if I have these fluctuating and diffusing interfaces, then I can ask the question, at which distance do they touch for the first time on the average? And how does this distance scale with system size? So this is the question that we have addressed in this paper here, and this is the question that I will talk about now for a couple of slides. So we can try to understand this in the following way. As I said, the physics of this problem is very simple. The two interfaces, they diffuse and they also fluctuate. Right? So the diffusion of the interface system, which happens through, in the liquid-solid case, through the attachment and through the ordering of molecules at the interface. This diffusion is described by a Brownian motion. In addition to diffusion, you have the fluctuations, and the fluctuations, they lead to the disappearance of the slab with a certain rate, and the rate at which this happens depends on their distance. Two interfaces that are close are more likely to touch in the next moment than interfaces that are distant. So how does this contact rate, this rate constant for contact depend on distance? Well, since the fluctuations are Gaussian, it makes sense to assume that this rate constant depends on the distance in this particular way. This is just something that I postulate here. It can be justified, for instance, for particular models of surface growth. But let's, for the moment, assume that I have some rate constant that depends on the position for this for contact, and once contact is made, the slab disappears, and therefore the probability, the survival probability of the slab is proportional to this rate constant. Now, this process can be easily described with a reaction diffusion constant. The U of x and t is the probability density for the distance between the two slabs, and this first term here describes the diffusion of the interfaces, and the second term is a loss term that is due to this reaction, due to the contact. Now, how does the solution of this reaction diffusion look like? It's easy to understand how it should look like. In principle, imagine that you have some position-dependent rate constant here, the k of x, and now I inject particles. I can imagine this, I can view this as the motion of one particle. I inject particles at this x position. Then what first happens, it spreads, and since the k of x is very small here in this region, nothing happens. But some of the particles, they diffuse towards this, the region where k of x grows, and this is where a reaction can occur. The rate at which the reaction occurs is, of course, the density at that point x, times the rate constant, and this is a function that is peaked. This function tells us where the reaction is likely to happen. It is peaked because on this side here nothing happens because the rate constant is so low, and on this side nothing happens because the contact has already happened, right? The rate constant is large here, so when the system approaches this region here, it will react and nothing is left for the other side. If I'm only interested to know where things happen, then I integrate over time, and this function here, the PC of x, is the probability that the reaction will happen at a certain distance x. Now, how can I compute this probability? This probability that the two interfaces touch at a particular distance x. We can compute this probability using path integrals. We write down the probability of a certain path that survives up to a certain time t, and by going to the continuum limit, you can show that this probability has corresponds to an action that has this particular form. And when you look for the most likely pathway, you find that it's exactly a Newtonian path that minimizes the action, a Newtonian path that lives in a potential that looks like minus the rate constant, the position-dependent rate constant. And for this Newtonian dynamics, there is a conserved energy which has a kinetic part and the potential part, and the potential is just minus the rate constant. And if this looks familiar to you, then probably because this is formally exactly the same problem as the instanton problem in the path integral formulation of quantum tunneling. And the reason is that this equation here is really a imaginary time Schrödinger equation, where the potential energy term actually corresponds to this luster. So this is something that you can solve by minimizing the action and expanding the pathways around this around the minimum action path. This gives you an analytical expression for the probability that contact happens at a certain distance x. And from this probability density, you can compute the most likely distance at which this x happens. It's a very simple expression where this w is the Lambert. The w function is the inverse of x times e to the power of x. Basically, for large x, it's the logarithm. And if you compare this solution here with the numerical solution of a particle diffusing in a rate constant landscape that looks like the gray curve here, then you find these curves here for the probability to make contact, and these are probabilities for different densities. So for different diffusion constants. Sorry, if the system diffuses slowly, then contact happens at large distances because the fluctuations have time to be large enough to make the contact. If the diffusion is quicker, if the diffusion constant is large, then the two interfaces can approach more closely before they touch, and therefore they touch on the averages at smaller distances. This solution here, this is interesting because this tells you that the most likely path has to speed up. The most likely surviving path has to speed up where the rate constant grows, right? Because it essentially falls down into this hole made by the inverse rate constant, and it accelerates here, and the system has to pass this high rate constant region quickly in order to survive. So this is really the same as the instanton in quantum tunneling. Now, in order to really understand how this touching distance depends on system size, we have to apply this theory to a particular model of surface growth. Here we chose a very simple one, the Edwards-Wilkinson problem model for surface growth. If you discretize this model, it's nothing else than a number of Brownian particles that are coupled by harmonic springs. And for this model, you know how the surface roughness, how the diffusion constant, how this prefactor in the rate depends on system size. You know, the scaling from capillary wave theory and from the decay of Fourier modes. So you plug this in, and then you find that you have a very slow growth in one dimension. Is not so slow, it's like a square root of L, but in 2 dimensions, really logarithmic growth that you find of this distance, which means that even if you have a very large system, the distance at which the 2 interfaces will get into contact is very small. How good is this theory? If you compare it to simulations, you find that it works very well. Here you have results for the 2D Ising model, for the 3 Ising.
Sorry, Christoph, maybe you have to summarize in a couple of minutes, probably.
Yes, I will be done soon. So also for the liquid gas interface, liquid vapor interface of Lennard-Jones, it works quite well. So now let's go back, if I may, for a couple of minutes. Let's go back to the melting of ice. So let's look at these trajectories that we start at the for a slab geometry at coexistence, and this is a trajectory where that actually freezes, but it's going a bit slow. I'll speed it up. So you will see that this trajectory will lead to freezing, and all these colors that are shown here denote defects that I'm going to discuss in a second. So what are the defects that can occur? And because I mentioned them because they play a role for melting. You can have interstitials or vacancies. You can have L or D defects. These are defects that violate the so-called ice rules. But then you can also have, and these 2 types of defects are rather mobile, and then you can have 5+7 defects and more complicated topological defects, where instead of having the usual 6-membered rings, you have rings with a different number of members. For instance, you can have 2 5 rings and 2 7 rings close to each other. This is a 5+7 defects, but you can have more complicated arrangements as well. Now, if you produce trajectories by starting them from the transition state and you analyze them, then you find that roughly you can separate 3 phases of the melting process. Namely, you start with the formation of topological defects. They can be quite complicated. And then in the second phase, L and D defects and interstitials and vacancy pair forms, and they are rather mobile and they move around, creating more defects. And that eventually leads to the melting. It would be interesting to discuss this in more detail. Let me just mention here that in the case of melting, it's not possible to really pin down a specific sequence of events that happen. Actually, there are many different ways in which the ice can melt. All of these but include at some point, of course, the formation of defects. And in most cases, you first start with the formation of these 5+7 defects that are and in later stages, you have the formation of mobile defects. So this basically brings me to the end. I'm sorry for having had to speed up at the end. I will be happy to answer any questions you might have.
Thank you, Christoph.
Thank you.
Yeah, nice talk. Shaboni Tarabdar asked, okay, let me go. So she asked that how do you take care of the boundary condition for the symmetry of the solid phase?
So, I mean, the simulations that we do here, they are, I mean, we choose a geometry of the box that is compatible with the geometry of the ice lattice. We do the simulations at constant pressure, of course, and that makes sure that ice can actually form. I don't know if this is an answer.
Okay, so Peter is asking that what is the effect of correlation between the surfaces? One would expect that fluctuating surfaces influence each other, certainly when close to each other.
So you mean the correlations beyond touching? This is something that we have neglected in this model, right? So we assume that the surfaces are completely independent from each other. That's of course not true. That's because there will be interactions between the surfaces which are not captured in the model. The fact that the model works rather well indicates that these correlations are not so important, at least not for the question of when these surfaces make contact.
Okay, so Taro Karmakar asked that I'm curious if the transition state definition for a finite size system in the coexistence setup is well defined.
Can you say it again? I didn't understand.
So I'm curious if the transition state definition for a finite size system is well defined.
I think as long as you can define the stable states, then also the transition states are well defined in the sense that these are configurations for which the probability to relax into either one of the stable states is roughly equal. And these configurations certainly exist, and these are the transition states, and this can also be defined for very small systems like the ones that we have studied here.
So, Christoph, my question was more on the finite size effect. Do you see any finite size effects in your?
On what?
Finite size effects.
I mean, in a sense, the whole process is a finite size effect. So I'm not sure exactly what this means. I mean, certainly the transition state that we from which we start here is an artificial transition state that
because more often sometimes you need to take care of this critical nuclear size.
So Tarak, I think this needs more discussion in the possible sense.
I'll write in the chat.
You may continue later with Christoph. And I think Amish wants to ask one question. Amish, go ahead. The last question I will take.
Hey, Christoph, really nice. I wanted to ask a question about the rate as a function of the distance between the slabs. And you assume a parabolic form for the barrier, which I think is certainly sensible. I wanted to sort of make connection to an isomorphic problem of capillary evaporations. You have two hydrophobic surfaces. You have a very similar kind of physics where you're looking at de-wetting between hydrophobic surfaces. And there we've also seen that the barrier varies parabolically, or it's a parabolic function of the distance. Mm-hmm. But that dependence seems to stem from, or to account for that dependency, you assume that line tension becomes important. If you only think about gamma A and PV type terms, then you have a linear dependence, right? And so I was wondering if you could comment on in this particular system where you don't really have an external surface per se, you only have an interface. What might be a line tension equivalent associated with this neck that you might need to form, right, for the two things to come together.
Yes, well, that's an interesting question, right? Because we have, I mean, so the Gaussian form of the reaction rate constant really assumes that the fluctuations are linear. But where you form a neck, you have something that's probably quite non-linear. Nevertheless, I mean, the model seems to work well. But this is something that would be interesting to study. I think you would have to be more careful, because actually you also need to study the statistics of extreme cases. So yeah, I don't really have a good answer for this question, but it's an important question, certainly.
Okay, so let's thank Christopher again for the nice talk. With this, we'll move on to the next talk, which will be presented by Professor Ioannis Kavrikides. He's currently the Bloomberg Distinguished Professor at the Department of Chemical and Biological Engineering, Biomolecular Engineering at Johns Hopkins University. His research interest is multi-scale computations and modeling of complex systems. He has developed in the past something called equation-free approach to complex systems. And now he is working on linking with modern data mining and machine learning techniques to develop something what he called an equation-free and variable-free approaches to modeling the complex systems. Today's talk is on the machine learning tipping points. So, yes.
Thank you. Thank you for the invitation, for the organizers. It is the second time that I missed being here. I really regret this. I was looking forward to it. Given that we've kind of taken 12 out of the 30 minutes, I was thinking of talking about 3 things. I'll probably try and talk about 2 things and see how much I can do. I had okay, this was supposed to be for fun. It's an economics-based, agent-based model. You have 50,000 agents that live between -1 and 1. And -1 and 1 have to do with whether you want to buy or sell. And 0 is neither buying nor selling. And there is all kinds of things about how they interact and how do you go jumping, going back to 0, selling and going back to 0, or buying and going back to 0. I will skip all over this and just tell you that you have 50,000 interacting stochastic differential equations. And what I'm going to show you is what they do. So I run them. And what you see here is a version of the behavior. These are the 50,000 agents. This is the PDF of the agents. This is the mean, and this is the fluxes at +1 and -1. Here you see that the agents look like a partial differential equation that goes to a stationary state. This parameter 42, I didn't tell you the details, has something to do with how much attention they pay to each other. If they pay 42 attentions to each other, everybody goes to a steady state. You go to 46.5 attention to each other, and then what happens is that they go okay for some time and then they explode. Everybody rushes to go to 1. So this is a place where you have a transition between normal behavior and a different, very different explosive basin of attraction. And you mentioned equation-free stuff. So 20 years ago, we developed techniques in which you run brief bursts of the agent-based problem, and then you do macroscopic calculations at the coarse-grained level. So you run the agents for a little bit, and then you take an integration or a Newton step for the coarse-grained reaction coordinate of the agents. Here, the reaction coordinate is not the scalar, it's the entire PDF of the agent distribution. You can use this to accelerate stuff. So what you see here is something that was called coarse projective integration. This is the CDF for the agents. You run them a little bit and then make a macroscopic run of the coarse-grained observables. You reinitialize the fine-scale simulation briefly, and you see there is jump. So the idea is that you save macro time by doing these brief bursts of simulation. That's not the important thing. The important thing is, and again, I am going very quickly through this, the important thing is if you don't have a macroscopic equation, you can still solve it without writing them down by doing brief bursts of microscopic calculation with the right initial conditions and then processing them nicely. It's not, again, so important what the algorithm is. Let me show you the result. What you see here is the parameter value. Think of it maybe as a temperature. It's not very fair. This has to do with how much attention they pay to each other, or maybe like the strength of an interaction potential. And what you see is a stable branch of solutions and then an unstable saddle type branch of solutions. And what we did, we were able to do the coarse-grained bifurcation analysis of this without deriving the macro equation, finding the bifurcation diagram. At the bottom, what you see is coarse-grained stationary distributions of agent, but stable ones. At the top, coarse-grained unstable saddle-type distributions of agents. So it's a bit impressive to find saddle-type distributions of agents that are stationary, because simulation will not go there. What's the idea? The idea is that if you find them and then you sit at the right transition state, at the right unstable stationary distribution, if you kick it a little bit downwards, it will go to the stable stationary distribution. And if you kick it a little bit upwards, then it will explode. So the idea is that one uses coarse-grained bifurcation calculations to find the transition states. And now, having found these transition states, you can do all kinds of things, like, for example, write coarse-grained controllers and keep the unstable solution stabilized, which is what you kind of see here. So use macro knobs to stabilize unstable stationary distributions. But what I really wanted to talk to you about is that if you go very, very close to this coarse turning point, a tipping point, then if you sit very close to it and you run the simulations, the PD is really, the partial differential equation for the density is really not a very good model. What happens is you see that you do have fluctuations, and at some point the fluctuations will kind of drive you to the other side and escape. So what's the idea? You go very, very close to the tipping point, which was discovered by the first coarse-grained round of simulations. And then what you do is that you find some good mathematics-based reaction coordinates close to a tipping point that's a turning point. What is a good coordinate? It's the unstable eigendirection of the saddle. So what you'd see here very quickly is to find the first coarse-grained round of bifurcation diagrams, find where the tipping point is, and then use math to suggest what would be a good coarse-grained coordinate, in particular, the unstable eigendirection of the saddle, and then go and identify an effective potential in this variable. You do this, and then you can kind of go ahead and find distribution of escape times and so on and so forth. The thing that is interesting is not so much that you can do that. This was done with Kramers-Moyal estimation, and then with diffusion maps and geometric harmonics for estimating the surrogate model. What was interesting here is that in addition to doing it, as I kind of told you, in a mathematics-inspired way, the reaction coordinate, you can also do data mining. Our particular poison is diffusion maps. And with the diffusion maps, you find that the escape is more or less effectively one-dimensional. And therefore, what you can do is that you can use the diffusion map coordinate now to learn the effective surrogate model. And the important thing of all of this first part of the chat is look at this diagram. It's a very messy diagram. It's supposed to be a straight line that you see here. Here is the effective coarse-grained coordinate. It says intuition. It's the one that is based on the bifurcation diagram and the unstable eigenvector. Here is the coordinate that comes from just data mining the results. And the important thing to see is that they're practically one-to-one with each other. So the interesting thing, if you want, is the comparison here of coarse-grained coordinates that come from math versus coarse-grained coordinates that come from data mining, and testing that they are one-to-one with each other. This is another tipping point example. This is a paper we did a few years ago before COVID, which kind of becomes interesting or important again. This is running a very large 100,000 network of people. They are infected, susceptible, recovered, but then the connections are adapted. If you know that your friend is sick, then you don't go and visit them. So you run this, you still have to find coarse-grained coordinates for it. Now the tipping point, if you look at it, it's over here. This is one of the parameters in infection rate, is a subcritical Hopf. So you do a coarse-grained bifurcation diagram on the first round, you find the subcritical Hopf, and now you see it's not just the same kind of usual escape from a saddle in one dimension. Now you need to escape from a crater in 2 dimensions. And what we do is that we first, to find course coordinates, we need distances between graphs. So we use graph metrics to find distances between graphs, do diffusion maps, find coarse grained coordinates. And maybe I will sit a little bit on this slide. Here, what you see is the coarse grained coordinates colored by the physically meaningful coarse grained coordinates, like the density of susceptibles and infecteds. What you're supposed to see with your eye is that the color is one, suggests that the physically meaningful and the data-driven ones are one-to-one with each other. So one of the interesting things is to think a little bit about interpretability of the coarse-grained coordinates. The second interesting thing is that instead of doing Kramers-Moyal and then using geometric harmonics to find the surrogate model, so a kernel maze method to find the surrogate model, what we've done now is that we have used neural networks that are templated on numerical stochastic integrators, Euler-Maruyama, Milstein, and Point, to identify the effective SDE, so that when you have the effective SDE, you can kind of go and do the rare event calculations with the surrogate model based on the effective SDE. And this is something that is the third thing that I wanted to talk about. I'm looking at my time, maybe I can make it. Well, what I wanted to discuss as a second subject, let me skip over this. A long time ago, since it is a conference where there's a lot of molecular discussion, I should throw something molecular also. We came up with Bill Gear, maybe 20 years ago, with something called computing in the past with forward integration, which is run your simulation a little forward, estimate an effective time derivative at the coarse level, and then take the problem backward. Run forward a little bit, estimate at the coarse level, and go backward. So this is effectively going backward in time, going up an effective free energy gradient, not in the directions that things explode, but in the slowest, most probable direction. You can think of it, it's a paraphrase, but it's not completely fair, but it is a way of kind of doing a sort of mildest ascent on the fly. Not exactly, but it's a comparable idea. And so what we did a few years ago with Gerhard and Roberto Covino and a number of people, Elio Chiavazzo was the first author in the paper, is to do an exploration geometry that is based on the-fly data mining and biasing based on coarse-grained geometry. Think of it as a revealed exploration geometry. What do? You run a little bit, and you see that over here. You do data mining and find that your behavior is effectively low-dimensional. And now that you have the low-dimensional geometry, you go to the boundaries of the low-dimensional geometry, do a little bit of differential geometry, bias the initial conditions, create initial conditions with Klum for the numerical method, and then run unbiased simulations again. So unbiased simulations, find the exploration boundary, perturb it geometrically, reinitialize and run unbiased, do it again and again. You can think of the effective free energy surface that you don't know is like a dark carpet in a very high dimensional space. You run a little bit, you do data mining of that, you go to the boundary of what you did. You need to find the boundary. There's good tools for doing that. Do a little differential geometry, create good biased initial conditions, do it again and again and again. And we call this intrinsic map dynamics because we use the on-the-fly revealed, if you want, geometry to go effectively up a free energy surface. You need to be able to simulate unbiased. You do that. You need to do data mining. You can do that. You need to find the boundary. Here we used alpha shapes. And then it's kind of important when you create the new initial conditions in core space, you can go back. You need to go back to the full space. There's a lot of work on doing that these days. And for example, does it using GANs. So we used to do it with umbrella sampling in the coarse variables, which were principal components at the time, local principal components, so Plum. This is doing it in alanine dipeptide, which is trivial. After 2 rounds, you fold the little thing. This is something that we did with Gerhard that was done by Roberto Covino. It is much more protein-like. There's an MGA dimer, and there was a long simulation, a long Martini simulation of the MGA dimer. It had found a few transitions. What we did, and this is the summary of the PNAS, is this picture. This slightly shitty colored part is the part that you find from a long, I think something like 6 months, Roberto said, unbiased simulation. Here you see, if you want 1 day of simulation, the times are not correct, but they give you a feeling. 1 round of simulation, data mining, find the boundary, extend, and then this is the second round, and then this is the third round, and even from the second and eventually in the third round, the dissociation of the dimer was found that had never been found before in the direct 6-month simulations by the Martin. So what is the point again? The point is exploration biasing, but not doing it with just blind active learning, if you have, reinforcement learning if you want, but doing it based on the geometry of the surface that you have so far discovered. This is kind of the fun thing that I wanted to show. Maybe this is the last time that I will show it. I wanted to share the sound, and I think I am sharing it. So I don't know how many of you remember seeing the Indiana Jones movie.
When they leap from the lion's head, they prove his worth. Impossible. Nobody can jump this.
Indy! And you must hurry! Come quickly!
It's a leap of faith. You must believe, boy. You must believe.
If you remember the movie, it's really fun what happened. Fun, but because of what he does, now. Out, what we do is that we actually see the path. So what I wanted to tell you in this is that metadynamics actually fills in the ravine with sand, while the kind of thing that we do, if you want, throws out just enough sand to cover the effective low-dimensional free energy surface. So the idea is that, again, you can use the geometry of what you've discovered up to now in order to make more parsimonious paths than filling the ravine with sand. The third thing that I wanted to tell you is something I was listening to what Professor Gordon was saying in the morning. It has to do with gauge invariance in data mining. How do we do our data mining? So as long as we observe different views of the same thing, the latent space that we're going to discover is going to be the same. This is something that we've been working on for the last maybe 4 or 5 years, and actually in a way for the last 10 years, but consciously the last 5. You kind of know that if you use kernel methods to do data mining, the important thing is the distance. Yes?
Nara, wie geht's? Bist du daran?
I heard somebody, but I don't know what they said. Was it for me?
No, you can go ahead.
No, okay. So think of the horizontal axis as being a divine space, like a Platonic space, the most beautiful way of representing something. And then we need distances between conformations. And then based on these distances, we can go on and do Gaussian process regression or kernel PCA or diffusion maps or whatever. Let's say that on the left axis is Janus, and Janus does not see the same thing that Plato sees or God sees, but sees something that is a distorted version of the truth. This means that the distances of the same observations in my space are different than the distances in the God space. However, if I don't only compute distances, but I also, do you see these little kind of circles around here? If I do a little jiggling of my simulations very close to the initial problem, so if I perturb the problem a little bit and look at how this perturbation ensemble looks like in my space, I can use the perturbation ensemble shape to estimate the slope of my own observation curve. And if I have the slope of my own observation curve, then I can scale the distance so that it looks very much to the fourth epsilon power, like the distance in God space. And if this is, I don't know, if this is Pratyush, and Pratyush has his own view and his own measurement device, and then he looks at the same two events, but now the distance in Pratyush space is really, really different. If Pratyush also observes the little jiggle around the initial and the final point and uses it to scale his own space distance, then both I and Pratyush can map to Platonic space and fuse our data to each other. So the idea is that it is possible to take very different observations of the same thing. If you want, I really am not a chemist, so forgive me if I say stupid things. You can take chemical information, spectroscopy information, molecular dynamics information. You observe it the right way, then it is possible to fuse all of these very systematically by doing the right data mining. If you look at the shape of this, it looks very much like a lens. I did it on purpose. I can take my observations and map them to Pratyush like light going through a lens. What is the necessary magic? The necessary magic comes from Singer and Koifman, and it has to do with perturbing your initial conditions and your final conditions systematically a little bit. And I told you that we've been working on it for 10 years, but not consciously. We had a paper with Singer and Koifman back then for finding good reaction coordinates this way, but we didn't really realize that this was gauge invariant data mining. And as I said, the magic is that you use not the usual distance metric, but you use a Mahalanobis metric, which is based on the local covariance of the noise, not globally for the distribution, but in the neighborhood of your particular measurement. This looks like neural networks. It is neural networks, but it is not neural networks in the sense of doing something. This is a neural network way of solving the same eigen problem. You take the data and you try and put them in a latent space, but in this latent space, the main characteristic is that the covariance of the noise at the initial point becomes a perfect circle. So you're trying to z-score the data. You try to find a perfect space in which the noise is perfectly diagonal and amplitude 1. This is a way of taking very different measurements and registering them in a systematic way. Whether you do it with eigen problems or whether you do it through a neural network solution algorithm, it does not matter. The name here is a local conformal autoencoder. It is an autoencoder, but it imposes local conformality. The main idea is you have this is, let's say, the Platonic space. This is one invertible measurement of the Platonic space. This is another invertible measurement of the Platonic space. The idea is that by doing this kind of data mining, you can turn them into things that are modular and orthogonal transformation. They're very, very easy to match. So this is a systematic way, if you can get the little perturbed measurements around the main measurements that you have, that you can fuse information and also hopefully also register, calibrate, and fuse models. Why is this important, I think, in our days? I think in our time this is important because everybody, given data, will make their own neural network or ML or gray box or whatever model of a problem. The different models by different research groups will more or less agree on the data. So the question is, are they the same models or not? And what I told you is a way to register between different models and establish whether they are diffeomorphic from each other, whether my calculation and your calculation can be calibrated to each other. So we had a paper on matching between different neural network models. It's been around for 2 years. You will forgive the old professor, the computer scientists say, what a wonderful idea, but the application, it should be on something that has to do with MNIST. It will not pass again in the conference. This is just sour grapes on my part. So I want to finish with something that maybe you will find entertaining. In Renaissance, people found how to do the right perspective. They found a way to paint exactly the way that the work looks to you. They found a way to make a model that looks exactly like nature. This was very painful, and you see that they took a lot of trouble to be able to make models that look very much like what happens in nature. But then photography came along, and then, you know, it was not just enough. You had to show the mood when you see something, and you had to have impressionism. What I really want to tell you is that if this is nature, this is the Vitruvian Man by Leonardo, then you would like a model to be like a perfect mirror. You would like it to show you exactly what you see. And the idea is that generally a model is a slight deformation of truth. It's a little bit off. I want to take this idea. So this is like a Luna Park mirror. You see a little distortion of yourself. What I want to do is to take this idea and reverse it. What if what we see is really a realization of something else, more perfect? So this is one molecule, this is another molecule, and this is the third molecule. They all kind of have qualitatively the same behavior. Why don't we find a mirror that allows us to map my molecule, your molecule, and the third molecule to a sort of prototypical normal form? I know that it sounds a little bit funny, but again, the idea is, how about sculpting our latent space so that it is beautiful? Beautiful might be linear, like Koopman. Beautiful might be integrable. Beautiful might be unitary. And so the idea is to not just ask for a useful latent space, but ask for a latent space in which the dynamics are Hamiltonian, unitary, integrable. Let me just say that one of the nice things about this is that if you have very, very different measurements of the same thing, then it is also possible to fuse them. So this is kind of where I wanted to end and say that well, as you see, I am much more of an algorithm person and not so much of a person that knows about the chemistry of the transformations, but I find very exciting the idea of trying to do the data mining from different sources in a way that the results are very easy to match, are matchable. Okay, that was it. I even managed to finish on time with but 5 minutes for questions missing. Sorry, I started late.
Thank you, Yanis, for really great talk. We have one question in the chat box. Lucy Delamote asked that, can you recover the equilibrium distribution from IMAP-D?
Yeah, thank you. Thank you for the question. So this is something that I always personally have okay, let me put it this way. If you can parameterize, if you have a nice parameterization of your low dimensional manifold, then you take a grid on it, you calculate the potential of mean force locally, and you reconstruct the thing perfectly. So yes, you can, because you have found the geometry, and now with the parameterization of the geometry, you can do local calculations and get local drifts and diffusivities in your effective Langevin. There is no reason for this search to give you an equilibrium distribution at the end. If this search finds the geometry, then you can get the equilibrium distribution by just post-processing. I'm not saying it's easy. I'm just saying, if you have good reaction coordinates, then you revisit them, put a grid, calculate local drifts and diffusivities, and get the effective potential. So you can get it, but it is not a result of the search itself. The search itself is not obliged to give you at the end an equilibrium distribution. Did I answer?
Yeah, I think she said thanks. So
thank you.
Answered correctly. Any other question from any other participants? Okay.
Okay.
If there is none, then let's thank Yanis for this wonderful talk. This will be the last talk of this session, which will be presented by Dr. Gareth Tribalo. He is currently a senior lecturer at the School of Mathematics and Physics at Queen's University, Belfast. And his recent research interest is using machine learning algorithm to understand high-dimensional molecular dynamics data and to enhance the rate at which the phase space is sampled in connection to biomolecules, materials, and clusters. And the title of his talk is Reconnaissance Metadynamics Writes Again. Good.
Okay, thanks. Can people hear me?
Yeah.
And can you see my screen?
Slides are fine. Great.
And the pointer, no, they can't see the pointer, but that's
Pointer
okay.
I didn't find yet.
Okay, let me just see if I can work out how to get a, no, I'll do without a pointer. It's
Okay,
fine.
okay, go ahead, no issues again.
Okay, so thanks very much for the opportunity to give this presentation, and thanks to people for sticking around to the end of the day. I know it's quite late, I think, over in India, so I really appreciate you staying up. So what I wanted to talk today about is some work that I've done recently in collaboration with Federico Ghiberti and Michele Ceriotti. And when I think of this work, it's sort of a revisit of something that we did 10 years ago. And so I want to talk about it in that context. But before I get onto that, I want to tell you my favorite science story from the COVID pandemic. So let's just go there. So I play clarinet in a wind band over here in Belfast. And when this COVID pandemic started, I was really worried about going to rehearsals, because what I thought was, you know, there you are playing in a wind band surrounded by all these wind instruments, and everyone is going to be blowing loads of COVID outside of the instruments, and everyone is going to get extremely sick. Other people are more curious than I was, and there was actually masses of research done on whether playing musical instruments spreads COVID. And what they found in this research is actually that the airflow out of most musical instruments is extremely low. And actually, there's very little chance that musical instruments spread COVID. And at this stage, you're probably thinking, wow, 2 years of lockdown have driven Gareth completely and utterly bonkers. What on earth is he talking about? But this is related to my talk, because when I found that out, I thought, really, this is something that I should have known. I mean, if you think about, what's happening there? Why is it not? Ah, yeah. If you think about the shape of like a trumpet or something like that, it's all bendy and the air is going to slow down as it passes through that mess of bends and tubes. And it actually turns out that if you blow through a trumpet, you can't even blow out a candle with the airflow. And I felt like this is something that I should know. And when Michele and Federico came to me and described this idea for this new algorithm that they developed, which was sort of inspired by this reconnaissance metadynamics things, I had that same feeling. So what I wanted to do in my talk was explain a little bit about what we did with reconnaissance metadynamics, how this has been updated, and sort of what that feeling of this is something that we should have known was about, in the hope that that might be useful to people, because I think it's easy when you're using these complicated machine learning algorithms to sometimes forget simple things. So I will show you how I will try and show you how we did that with the development of reconnaissance metadynamics. So with that in mind, I'd like to take back in time 10 years, there we are, to the way that I was presenting my work in 2010. So I do these metadynamics simulations, these enhanced sampling methods that are based on biasing. And when I think about these and think about sort of classifying the ones that I really know about, I think in terms of there are two decisions that we have to make. So the first is, what collective coordinates are we going to use? And then the second question is, how are we going to distribute bias along those collective coordinates? And I break this space up into this area up here. We're going to decide what collective coordinates we're going to use using basically thinking, a carbon brain, and we're also going to decide how to distribute the bias along those coordinates by thinking, and that's a kind of umbrella sampling method. And the nice thing with metadynamics in theory, or at least as I supposed in 2010, is that the thinking about how to distribute the bias, you delegate to the computer, because the computer looks after that for you. So what I thought naively in 2010 was, you can use these machine learning algorithms to also discover your collective variables. You then combine that with metadynamics and you end up in this sort of nirvana where the computer is doing all the thinking for you, and all you have to do is run the computer, do the analysis, write the paper, and bask in the glory. So that was what we were trying to do. And the way, so how are we actually thinking that we're going to do this? So imagine that I ran a simulation of this Leonard-Jones 7 cluster. What you would see, and this is a movie, but for some reason it isn't working, I don't know why, sorry, is it wouldn't fluctuate much around that minimum. And we know why that is, why we see those boring dynamics. We know that there is an energy landscape that looks something like this. There's a big barrier, we're stuck in a basin, and we're just fluctuating around that minimum. And our idea was, okay, this is really boring. We want to see the rare event, but we're finding out something from those boring dynamics about that basin. We can take the information in some high dimensional space. We can calculate ensemble averages, even if we have a short trajectory. We can also calculate fluctuations, and we can use that information on the average position and the local fluctuations to define some sort of bias that we can then use, and that targeted information to basically eliminate that basin from consideration and to force the system away from a particular configuration. And that was our idea starting out with the development of this method. Sorry, I've got a bit of a sore throat. So that was where we started, but what we saw very quickly with these things was behavior like this. So we actually saw basin hopping events in these simulations, and it no longer became meaningful to fit that dynamics using a single Gaussian. And really that's the first point where this should have given us pause. So I'll let you think about that as I carry on talking to see if you can work out what the conclusions are. But we still had this idea, so that we could fit the local distribution with these Gaussians, and actually the fact that we're seeing between multiple basins wasn't a big problem, because we could use a sort of Gaussian mixture model to fit the dynamics instead of fitting it to a single Gaussian. So I've got a movie here showing you what we did. In this figure, you've got an energy landscape there, which is the contour plot. Then you've got a series of fine points that I hope you can see. Those fine points come from a trajectory that we've run on that energy landscape. So that's the information that then goes into our Gaussian mixture model. And what our Gaussian mixture model does is essentially says, right, take that trajectory, so those little gray dot, those little sort of black dots, and fit that distribution as a sum of Gaussians, okay? And what you can see is that when you fit that distribution using a sum of Gaussians, you nicely find that the Gaussians that come out of that fitting sort of correspond to the positions of the minimums in that energy landscape, even though, as I said at the start, we've not really provided any information about that energy landscape other than through the trajectory to our algorithm. So how does that work in the context of the algorithm? So we all know how metadynamics works. So it's an extension of MD. We know that in MD you calculate the forces and then you move the atoms according to those forces. And all you do in metadynamics is that every now and again you make some change to the potential. So you add a Gaussian in these methods. So our idea was, in addition to doing the metadynamics things, what you're going to do every now and again is collect the trajectory and do this cluster analysis on the trajectory, and that's going to identify you new CVs to bias and to force yourself away from. So putting that all together, here is how reconnaissance metadynamics works in all its glory. So you run a molecular dynamics simulation, you see that during that molecular dynamics simulation, you're trapped in a basin, you then run the clustering, you identify that basin, you add bias when you're within a certain distance of that basin, and thus quickly eliminate it. And thus you can go and start to quickly explore these other features in the energy landscape. So you see, we're quickly exploring each of those features one at a time. And if we allow this movie to run on, we eventually get to a sort of flat potential and rapid diffusion all over the place. We eliminate each of those features one in turns through this process of alternating running dynamics and then clustering. Okay, so I don't need to carry that on. Hopefully everyone's got the idea. So that's it on a 2D potential. We also did a study to test it. We did a Leonard-Jones 7, but we tried to make this problem more difficult by basically supposing that each of the atoms was indistinguishable. So we used 7 collective variables here, basically the coordination numbers of each of those atoms. And again, we're doing exactly what you've said before, but now we're doing the clustering in a 7-dimensional space. And we're identifying these features. And the important thing to realize is that this structure that has the yellow atom in the center, in our representation of that data, is different from the structure that has the blue atom in the center, because we haven't taken into account interchange symmetry. Okay, so hopefully that's enough of that movie for you to get the idea. So what I think was the main result that we showed in that paper was this figure here, and I still think this is cool. 10 years later, what we've got here is each of those planes represents the basins that we found by doing the clustering that have a different atom having the largest coordination number. So these are the first plane is the one, atom 1 has the largest coordination number, the second plane, atom 2, has the largest coordination number in those structures. And then we've got some simplified representation of that. And what you can see, which I think is quite impressive, which I think is impressive, is that we really have kind of identified, we're seeing that each of the sets of basins that we find in each of those clusters are similar. So we're identifying the same features when we run this algorithm. We're identifying that there is the indistinguishability when we run this reconnaissance metadynamics algorithm. So there's definitely something in using these Gaussian mixture models in combination with a sort of metadynamics bias. But we sort of tried it for this system. We tried it for proteins in vacuum. We did a bit of more stuff with some bigger clusters. But when we tried to take this to studying proteins in water, we never really could get anything sensible out of this method. And so we sort of abandoned it and left it as a sort of dead end. But Michele and Federico have repurposed this in the last year. So now let's talk about what they did to repurpose it. And I think this process of repurposing, and I need to talk about why I think we abandoned it and why we felt that maybe this wasn't such a great idea, which is the fact that there was this thing that we had to do, this fudge that we had to introduce in the method that was slightly dubious. So what I showed, these are some stills from the movie before that I showed you earlier. So what I said we were doing was, we run the dynamics, we collect the data, and then we do this clustering and we identify these basins. And then what we do is we start depositing bias when we're within a certain cutoff of the center of the basin, because we know that the distance from a point becomes a worse CV as we get far away. And we use the hard cutoff for that distance. And what you'll see in the movie is that these basins kind of expand. So the size of that hard cutoff changes. And the reason that we have to expand those basins is that if we don't, what we see is behavior like this. So you deposit a bunch of bias here, and that creates a load of minima around there, which is then a mess when you try to do the Gaussian mixture model. Now that's a figure from the paper, so we were completely upfront about the fact that we were doing this. But it was always a bit kind of there was always that question mark about whether or not this was a good idea and how to set the parameters associated with the expansion of these basins. And that's why I think it sort of hit a bit of a dead end with this method. So if you look at the literature, other people have used these Gaussian mixture models in the umbrella sampling community. And the way that they generally use them is they take that Gaussian mixture model and they use that as a representation of the histogram. So they say, okay, we'll fit this Gaussian mixture model, and then that Gaussian mixture model is a representation of the probability distribution that we're sampling, and then we can use that as a bias. So they actually recognize that what you fit with the Gaussian mixture model is a probability distribution. And I think that's the first step in this new method atlas that Federico and Michele have developed and that I've implemented in Plumed. We write explicitly that what we're fitting is this probability distribution that looks something like this. So in this expression, just to be clear, these are normalized multivariate Gaussians, the G's there, and we've got a sum over those. We've then got a weight for each of those Gaussians. These weights obviously sum up to 1, and that weight tells us how much of the trajectory is in each basin. And then we have this final quantity, pi0, which is a sort of background basin, if you will. So it's some quantity that tells us whether or not we're not near any of the Gaussians that are there. So I'm illustrating it with that that outer Gaussian. That's a little dishonest because this does not really correspond to a mode in any of the features. So we use that expression. So with that probability distribution in place, what you then do is you sort of fuzzify the basins. I'm just going to move this for a second so I can actually see my slides. So you fuzzify the basins using this expression here. And if you look at that expression, the top line is a probability. So this is the probability of the data point being generated by the kth Gaussian. Goodness me, what the hell? This is the bottom line is a total probability. So this thing looks a bit like a sort of Bayes theorem. And this quantity here that you get out, there's then the probability that point S is in the kth feature. So if you calculate this for these 3 different modes here, for the square point, what you get is that phi1, the blue, is equal to 1, and phi2 and phi3 are equal to 0 because you're inside the blue basin. For the circle point, you get that phi1 is equal to 0, and phi2 and phi3 are equal to half, and then the last one gives you a third each. So what we then do is we use that to construct a local bias. So we build a local bias that looks something like this. The total bias is just a linear combination of some local biases, and those local biases are weighted by this fuzzified switching function that switches between our various different basins. And what are these local bias? So you, again, if you calculate the total bias at this time, you see that you get a contribution from those 3 local biases in accordance with where you are relative to each of them. So the form for this local bias looks something like this. If you look at this expression, this is a sum over the history. This is our beloved well-tempered factor. And this is a Gaussian centered on the instantaneous value of a local CV. So those first three terms are basically just your familiar things from metadynamics. And then this final term here is basically splitting the weight of that Gaussian between the features that you've identified using your Gaussian mixture model, okay? So what are these local biases? Well, this S that comes in here is just a vector that contains a lot of CVs that might be of interest. And then to calculate this CK, we could do something like this. So this is going to be the center of our features. So the local Gaussian, the multivariate Gaussians that we've identified. And this here is a local covariance matrix. So this whole expression is a Malohn-Mobius distance. Or alternatively, what we can do is we can diagonalize that local covariance, put the eigenvectors in the numerator like that, and the eigenvalues, square roots of the eigenvalues in the denominator. And this quantity then is basically the projection of on the principal eigenvectors of the local covariance. Okay, so putting all of that together, let's have a look at how the method works in 2D. So here we've got a 2D energy landscape that we're going to investigate. We fit that using a Gaussian mixture model. We take a trajectory from that, fit it using a Gaussian mixture model. We might get something looking like this. So you see we've got 3 Gaussians that correspond to our 3 features, and the collective variables that we're going to use here are represented by those arrows, which are the principal eigenvectors of those local covariance matrices. So this shows you the theta values as a function of time. So you see that during the trajectory, you basically switch between these different modes, and those switchings are almost instantaneous. And then last but not least, this is how the bias grows. And if you've done any metadynamics, this looks a lot like how a metadynamics bias grows in general. The points here are colored according to basically the value of the local bias that you're calculating, because the bias is the sum of these 3 local biases. So you see initially you're inside this red basin, so the bias is felt as the local bias for the red basin. Then you switch to the purple basin, so you build up bias in the purple basin, and so on throughout the simulation. Okay. And the really nice thing here is that in the last 10 years, reweighting of metadynamic simulations has moved on. So we can now extract the free energy from these calculations using reweighting, which we could never do with reconnaissance metadynamics. And in fact, this first figure that I showed you here, the black lines are a reference calculation that we did with parallel tempering, and the purple lines, the filled contours are the free energy surface that dropped out when we did the reweighting of the metadynamics. And you can see that these 2 things, these 2 estimates of the free energy are very, very close. Okay, that's great. 2 CVs is wonderful. It's lovely to study these model systems, but it's hardly impressive. But we can go to 6 CVs. So we've got, again, an analytical potential that we've done in CVs. We've weighted it down to 2 of them here. And you can see, again, if we compare the parallel tempering result with the result that we get from the reweighted Atlas simulation, we're at a pretty good match. You can also look at the convergence. So here we have measures of convergence. We've got various flavors of Atlas there, which are the rapidly converging ones. The only thing that's really interesting in that diagram is how much faster that we converge than 6-dimensional metadynamics. It's not surprising. No one would expect metadynamics to work particularly well with 6 CVs, but this Atlas thing works much better, and we actually can get meaningful free energies, even in these high dimensional spaces. Sorry to brush over the details there. If people are interested, I can send you the references. What about real systems? So here is, we've done Leonard-Jones 38. So we've done this with 8 collective variables. We've got 3 free energy surfaces here. The red dashed lines are from metadynamics with 2 CVs. The contours are from a parallel tempering reference, and the solid plots are the Atlas with 8 CVs. And what you can see is that the Atlas is getting much closer to the parallel tempering reference there, which is very nice. And these points here that I've illustrated, these are the centers in our Gaussian mixture model. Now, at this stage, you're probably saying, yes, but in order to do this, you need to actually have a trajectory that has explored all of phase space. And that's the whole problem, is getting this thing to explore phase space in the first place. If you have that, then the problem is solvable. But this is actually where this Atlas thing is really neat, because we aren't reliant on good sampling to fit. We are reliant on good sampling to fit the CV, but we can iteratively refit the Gaussian mixture model using a method something like this. So we start off with an unbiased simulation. We produce a Gaussian mixture model from that unbiased data. We then do the Atlas for a while. And then we redo our analysis, having reweighted that free energy surface and create a new Atlas bias. And that's precisely what we did for this Leonard-Jones 7 problem. So we actually did 3 rounds of iterating this thing, this method, the different calculations. And the really nice thing, I think, is that if you look at these formulas, you have this pi0 term, and you can calculate a corresponding θ0 term. And this θ0 term is basically telling you whether whether there is a high probability that you are not close to any of the features that you've identified with the Gaussian mixture model. And if you find that the sort of time interval, so the amount of time you're spending in configurations where that value is high, is large, then what's that suggesting to you is that there is some feature in that space that is a kinetic trap that you've not identified, and you probably should go and refit the Gaussian mixture model in order to identify that feature so you can put a suitable local bias there. So this is, I think, a really nice feature of the method, because it means that as well as being able to sort of converge the free energy surface, you can also think about there is a parameter that helps you converge the CV. So one final example, just to show that it works for proteins. We ran the proteins using all, this is ALA4. We ran using all the backbone dihedrals for this system, but you can re-rate out as a function of number of hydrogen bonds and radius of gyration. That's no problem. But another nice feature is that if you don't really know what CVs to use, what you can always do is calculate the relative free energies of the features that you've identified using the Gaussian mixture model, and get some idea of the relative free energies. So that's this atlas idea. I just want to finish by coming back to this business of the musical instruments and COVID. So why do I think this story is like that? Well, if you remember, what I said is that, you know, it should have been obvious that there's not high airflow out of a musical instrument. That's what I felt like. I heard Simon Rattle on the radio. He said, you know, what comes out of a musical instrument is sound and not air. So what's the deal with this reconnaissance metadynamics thing? Well, if you think about how metadynamics works by accumulating histogram and using that histogram to bias the sampling. That's what we say. It doesn't work by eliminating minima and basically forcing you out of them, as I sort of started off with. And if you think about what I've told you about how reconnaissance metadynamics works, and you think about that in terms of trying to define a histogram, the problem there was that we hadn't defined where all the points would go in the various bins. So, you know, there were large portions of trajectory that weren't going into any bin in our histogram. So, you know, that's why I say this problem. This is what I felt when they told me about this method was, oh yeah, of course, you need to basically calculate your histogram properly. So, you know, even though we now use all these fancy machine learning methods, don't forget the basic ideas. So with that, I'll just thank my collaborators as well, because the other similarity between this work and my clarinet playing is that I've had to do my clarinet practice for the first time in about 20 years during this COVID pandemic. I am horrible. No one should listen to me play on my own. The same is true with science. So I really have to acknowledge Michele and Federico, who did all the work here, and everyone who's ever added any functionality to Plead. And with that, thank you, and thank you for your attention.
Thank you for this wonderful talk, Gareth. We have one question in the chat box. Satyabrato Bandyopadhyay. He has said, how can we determine the optimum value for the number of Gaussians in case of Gaussian mixture metadynamics?
So you can look at the paper but there are these, because I can't remember exactly how we did it for this one, but when we were doing reconnaissance metadynamics, there are these Bayesian information criteria, and there's another information criteria. And these work by basically when you increase the number of parameters, the model will always improve. But what you do is you do something like Occam's razor, and you add in a cost for adding in more parameters. So by adding in more parameters, you're making the model more complicated, and then you remove those.
Yeah, also he asked something interesting, that whether you can actually get the kinetic information as you get it from single Gaussian metadynamics run.
That is can I get kinetic information? That is an interesting question. We didn't try, but in theory, yes. And again, I think if you take those features out, that's a sort of natural way of thinking about what the kinetics of transition between those various features. Can I add one other thing that I forgot I meant to say in my talk?
Okay, sure, go ahead.
Yeah, so I actually have a position available at the moment. And if anyone is looking for a job, please do get in touch. I will post the advert in the chat in a minute before the end of this meeting.
Okay, so is it a position for postdoc or PhD?
It's a postdoc position.
Okay, great. So the next question from Andrew.
Talk, I really enjoyed it. I just wanted to sort of come back to something you mentioned earlier, that recurrence and metadynamics had a bit of a problem with explicit solvent. And I was wondering if the new method sort of helped solve that.
We haven't tried it on a protein with explicit solvent. I think it's not necessarily that the problem was with explicit solvent. I have this question, and I never really know I don't know how to answer it, but I think some of these systems are very easy to solve. It's very easy to get out a good sampling, even if you put in a terrible bias. Now, I have no way to measure what makes a bias terrible and what makes a problem easy or difficult to solve. I think it's an interesting question. Like I said, no idea how to answer it. But yeah, some of these benchmark systems that we do, I mean, for example, like the Leonard-Jones 7 example, if you do that as a function of the first, the second and third distribution of coordination, second and third moments of the distribution of coordination numbers, I have done this putting in what I know are terrible biases that make absolutely no sense, and I still get sampling of all those different configurations. And I think the problem when you go to the explicit solvent is, your bias is, the system is more sensitive to a bad bias, if that makes sense. But I don't know how to quantify that. If you've got any ideas, I'd be fascinated to have a talk, because I think it's an interesting sort of thing.
Okay, so Nissan, please go ahead.
Hi, Gareth, very nice talk. Have you tried to couple this with some replica exchange techniques? Maybe to have multiple replicas exploring, because this would be working pretty well, right, with your technique?
Yeah, we haven't tried it with multiple replicas, but that's certainly something that can be done in the future at some point.
I have one more question, Biman.
Yeah, go ahead, please.
Maybe also just, if you could also try on some of the toy systems like tripeptide or pentapeptide, we could also compare. We are generating a lot of reference data for these systems, and so our record is that in 1 nanoseconds we have quite a good converged free energy surface in the 4D space for alanine tripeptide. So I'd like to see if it can be compared with your technique, and maybe something we can communicate. Because this tripeptide, pentapeptide, I think these are very good systems to try, and where we can try this replica exchange as a reference, compute L2 error, on the replica exchange data. So we have some microseconds data also on these systems. So we could compare it, and we can use this as a benchmark system for other techniques as well.
Yeah.
There are only very few techniques for looking at high dimensions, right? So
yeah,
worth establishing. Okay, thank you.
Okay,
so Gareth, am
yeah.
I right in understanding that basically you are completely trying to bypass figuring out the slow collective variable problem and saying I will just deal with as many collective variables I need?
Yeah.
But if you are missing out on something slow, you are not solving that problem, right? You just need to.
No, exactly.
More.
No.
Yeah, that's for sure. Okay, so thank you, Gareth, and
No
all
problem.
other speaker of this session for wonderful talks. And over to Nishant.
Yeah, thank you all, and I think we'll meet again tomorrow in a few hours. So tomorrow for Indians and tonight for Americans, and maybe for all others who are missing out the morning sessions, Indian morning sessions, we have the videos available in the YouTube link. I can. Anji, are you online? Can you put the
Yes, sir.
in the chat box, please post the link so where you can see all the videos until now.
Sure.
Also, can you please send this to the emails also? Like
yeah, right. I'll do that. Yeah. Okay. Also, one more announcement is that tomorrow's brainstorming sessions, please don't miss because it's going to be a lot of thrill. Alessandro is working hard for making the brainstorming sessions exciting, and the brainstorming sessions are the kind of the highlights of RARE meetings, so please don't miss it. And last but not least, I'm just sharing a link of photos from the previous RARE meetings Pritish has been sharing. So with that, I think we can stop.
Okay, thank you. Thank you
everyone. Bye. Thank you.
For anyone who wants a job, I put my advert in the chat.
So yeah.
Make sure you take it away because there's no record of the chat.
We are saving the chat.
Okay.
So the chat is available in the YouTube video itself.
All right.
So if you look at the video details, you will find the link to look at the chat.
Great.
Yeah.
Okay. See you, Nishant.
Bye.
See you, Gareth. Yeah.
Bye, Andrew.